Good morning, everybody. I'm very pleased to welcome you to this workshop. Actually, the workshop started 2 days ago, as you might know, with the organization of a summer school for students. So we are here and we are very pleased to launch this workshop about underground storage and geoenergies and all the problems which are with the underground storage facilities of a certain size. So these workshops have been possible with the financial support of the Energy for Climate Interdisciplinary Research Center of the school, where the LMS is part of the center with different types of operations. So one operation is sustained by Alexandre Dimanov, that you have here, and he can tell you directly what it's about. We have other problems related to batteries, and our colleagues who are doing meteorology, they are having a lot of problems about the climate. So you see here a number of logos of the organizations which helped organize this workshop also. The laboratory of École des Mines, the laboratory of Navier, at the École des Ponts. You have the French Rock Mechanics Society, and you have also Benoît BROUARD, who is one of the organizers of the conference. The other names of the organizing committee which are here, which I also use the occasion to thank, are Laura Blanco-Martin from École des Mines, Philippe Consenza, who is from Université de Poitiers, Jean Sulem for Laboratoire Navier, Alexandre and myself from the LMS, and Benoît BROUARD, which has his own independent business. So I wish you a very good 2 days, and I will be again with you on Friday for the day dedicated to Pierre Berest, which will be held not here, but at the École des Mines in Paris, which is near the Luxembourg Garden. So thank you very much, and have a nice day.
Thank you, Ali. So first, good morning and welcome to all of you. I'm really very happy and proud to welcome you here at this workshop conference, whatever we decide to give as a name. Just a few words, okay? We are not really in hurry, so just a few words to complete what Andre already said. Okay, this Energy for Climate Interdisciplinary Center exists since 4 or 5 years only. It started as just a little, I would say, clustering of researchers of different labs from the École Polytechnique, and Philippe Robinski, who is a meteorologist, so director of the LMD, Laboratoire de Mécanique Dynamique. He was working also with Pierre Berest, who gave support in the very beginning, and this is why, okay, when Pierre passed away last year, so we decided that in any case we should find the occasion to organize a conference in his memory. And Philippe Robinski said, okay, Pierre was right there, right from the beginning. Well, with myself, but Pierre had a little bit more scientific weight, certainly. So he said, okay, we give full support to organize, not a day or two, but let's make it larger. So summer school for students and conference, more classical conference, and a specific memorial day that will be held at the École des Mines, since Pierre came from École des Mines. And okay, this is how now we are here. But of course, the topic of this conference is well, all about energy storage. So this center, Energy for Climate, is training actually interdisciplinary approaches. So combining even socio-economical research and aspects, harvesting renewable energies, and at some point, development of smart grid systems, all kinds of approaches that could, help to the energy transition. And among these different aspects, of course, there is the key point of storage of energy. So there is different type of storage of energy. Okay, what we are specifically dealing with today, and what Pierre is actually promoting at the beginning of this adventure, is underground storage, mass storage of energy, any kind of underground energy. Could be compressed air, could be hydrocarbons, say maybe now synthetic gas or hydrogen. But although we are speaking here about energy storage, geoenergies, underground storage, I mean, I include in underground storage also sequestration, CO2 sequestration, for example. Not directly energy, but it's in the loop of these efforts for limiting the global warming. Okay, so this first morning session will be opened by a presentation by Professor SPIERS, who knew Pierre Verrest closely, and who was with Janos OAE, the very first one to immediately sign up for this conference as soon as I mentioned, we're organizing something. Said, okay, we're here, and so I'm really very happy to introduce Chris SPIERS. Unfortunately, she's not here today, and Chris will certainly say a few words about this. And after his presentation, we'll have the pleasure to listen to Joy Schmerz, who worked with Janos OAE, who was with Chris SPIERS and Pierre Verrest, probably, the most famous specialist in rocksalt mechanics. So.
Well, good morning, everyone. Thank you, Alexander, for the introduction. And following the summer school and the last couple of days, I'd like to say thank you again to the organizers and to E4C for setting up this very special meeting to remember Pierre. I knew Pierre since the early 80s, and at that time I was working at Utrecht University, where I remained my whole career, together with Janos OAE, who we tragically lost in a climbing accident just 2.5 weeks ago. Janos and I were working on rock salt, and we went to the early salt mechanics and salt mech conferences. One of the, I think it was the second one in Hanover. I couldn't remember if it was 1983 or 1984, but maybe Gorechi just reminded me it was in fact 1984. So that's where Janos and I met Pierre, and we were. I'm going to tell you a little story about that, and I'll show you a couple of pictures before I get into my presentation. So here's Pierre. That's really how I remember, and this is the official photograph. I didn't have another one, but yeah, you see so many aspects of his personality in that picture. Yes, it was 1984. He was wearing a tie. He was very sharp, very sophisticated. Elegant talk, but just Pierre, that's what he was. It was just wonderful. And so around about that time, this is a little earlier, 1982, you see on the right hand picture there, Janos and I was a postdoc. Janos was a PhD student in Utrecht. We were setting up the first Instron machine in our laboratory at that time. And poor Janos lost his life just a couple of weeks ago. This was a recent picture of him. So the little story, I go back to Pierre's picture for a moment. The little story was this. Janos and I were working on rock salt and finding all these new effects related to water, which to us seemed absolutely obvious. These effects must be there. We had background more in geology and material science. It seemed to us obvious there must be these effects of water. And we went to these early conferences and nobody believed us. Nobody believed us. Engineers from a not very far away European country said, but if you have a saturated solution, brine present in salt can't possibly dissolve, so this can't be right. All this stuff you're talking about can't be right. And it was widely, actually even venomously rejected, except for one person in this group, and that was Pierre. Pierre welcomed us into the community. He was interested in the results. He thought there was something in it, and it stayed with him. We remained in contact for our entire careers and worked together on these things. And he was a friend, a wonderful scientist, a wonderful teacher, and a wonderful person. And Janos was also a very close friend. I met him in 1978 when we were students. He was a very close friend, very close collaborator, and I'm going to miss them both really. Okay, so let's come to my talk now. So this has a tone of reminiscence as well, okay? So I'm going to talk about the creep of rock salt at low stress. And here is my little subtitle, which is important to emphasize now. I'm going to talk about the past, the present, and the future of this very controversial topic, okay, for creep at low stress. And I'm going to tell you about the absolutely game-changing role that Pierre played in, I think, finally resolving this controversy, okay? I'm going to get into the very basic science, how it developed, so I'm going to show you results that are years and decades old, and how the situation is evolved to what it is today. With thanks to Janos and my colleague Peach at Utrecht, and a more recent colleague, Susanne Hanks, for material I used and for a few slides and things like that. So here's rock salt. I showed this at the summer school as well. It's a fantastic plasticity. It's a wonderful material because of its high ductility, its low creep resistance due to dislocation plastic processes, and because of its high solubility and its ability to dissolve and reprecipitate and heal cracks. It has a tremendously low porosity and permeability. It's just a wonderful sealing material. And that means that it's a very important geological resource. It has all sorts of applications for storage. So let's look at a few of those quickly. So how important is rock salt? Besides solution mining for the chemical industry and table salt and all the rest of it, it really is a wonderful material for creating caverns for oil and gas storage, for storage of renewable energy in the form of hydrogen or compressed air or even underground hydroelectric installations. It has for many, many years been in the picture for isolating radioactive waste, of course, and it is one of the most important sealing rocks in the geological column for trapping hydrocarbons anyway. Right? So its sealing potential has provided the human race with vast wealth and vast opportunities for the future, which we have to assess, of course. So if you look at these sort of applications, storage of hydrocarbons perhaps, or syngas, and storage of renewable energy, hydrogen, compressed air, radioactive waste, we need to assess the performance of these systems and the risks that they may pose. So what do we need to do there? So of course we need to conduct geomechanical modeling studies and transport studies. A key element of geomechanical modeling, of course, is creep law, describing the creep behavior of the salt. And I'm going to talk mostly about steady state stuff today. Also very important are constitutive laws describing damage, permeability, evolution, very low effective mean stress, for example. And I'm also going to emphasize that there are two timescales to think about here. There are the relatively short operational timescales for facilities like the storage caverns. But then there's the long-term stuff, the long timescales. So we're talking here essentially about high stress regime and the long-term low stress regime. As I said in the title of my talk, I'm going to be really emphasizing the low stress behavior, the long-term behavior. That is very relevant when we think about things like abandonment of caverns. Okay? So when you abandon a cavern, you're probably going to shut in brine inside the cavern, and the salt will converge, the pressure in the cavern will go up, the deviatoric stress will go down. In the further field, they'll be really very low. So the evolution of that system will be determined by the long-term creep behavior of the salt to a large extent. The same goes for for the fate of the brine that is in such a cavern. Whether it will ultimately cause hydrofracture or perhaps permeate the salt or some sort of hybrid. So these are some of the long-term aspects. The low stress period of salt is not relevant only to the long-term behavior, but that's what I'm going to emphasize today. Okay? Right, so let's go back to the 1980s. So this is the past part of my presentation. All right? So I show here some data, some creep data, steady state creep data on rock salt, obtained in the temperature range 70 to 80 degrees, and it's plotted in a log stress, log strain rate diagram with 10 to the minus 12 strain rate, 10 to the minus 12 per second strain rate here, 10 to the minus 2 here, so it's getting slower this way. And already in the early 80s, there were tons and tons of data on creep of salt at steady state or approaching steady state. And much of that data could and still can be fitted very well with the classical power law kind of relationship, with an end value of about 5 or something, and varying between 3 and 7. But when Janos and I looked at this stuff in the early 80s, we thought, well, hang on a minute, we know from geological stuff, natural salt flows actually pretty quickly. And at natural stress levels, also things like salt baths, information from some, very few at that time, but a few bits of information on some cavity closure and things. We felt, well, hang on a minute, you can't explain natural flow rates at natural stresses of a few MPa. So this would be 1 MPa, 10 MPa, 100 MPa on this long scale, right? But down at these low stresses, which we could demonstrate were actually operative under natural conditions, the strain rates are kind of a bit too fast to be, or a lot too fast to be explained by this. If you extrapolate this, you're not going to make it. Right? And that led us to think, well, there must be another process. Or perhaps, there's some we don't have a proper physical basis for this behavior, not extrapolating it. So that is what got us thinking about what seemed to Janos and myself absolutely obvious. There is water in salt, it must have something to do with that. So, what controls creep at these low stresses in salt? And Janos was an absolute master in looking at the microstructure of natural salt. And he and I worked on that together. This is a reflection optical micrograph of a section, or a cleaved fragment actually from, it's not correct. This is a polished section of Avery Island rock salt, and you see these subgrain structures, which is characteristic of dislocation creep, which is the classical explanation for this power law type creep behavior that is seen in creep tests on rocksalts. Okay, so this kind of data quite clearly has long been associated with some sort of dislocation creep process, and you see evidence for that in sections of naturally deformed salt, okay, from the Avery Island Dome. We also looked at gamma irradiated salt samples. Gamma irradiation precipitates particles of sodium which turn the salt blue, and they decorate the substructure and they make visible differences in point defect and impurity content. And what you see in this is a transmission micrograph, what you see in there is that besides these subgrade structures, which are evidence of dislocation creep, there's very clear evidence for crystal growth going on there. These are overgrowths. This indicates dissolution and reprecipitation processes going on in this naturally deformed salt, which would, we know from the size of these subgrades is related and known from empirical relationships, determined in experiments. We know what stresses are associated with this. This is down to the level of about 1 MPa units on the street. Okay, so naturally deformed salt deforming at those low stress levels shows clear evidence for dissolution precipitation processes as well as for dislocation. All right, so Janos and I began to think, okay, this water has to have something to do with it. It must play a role here. And indeed, all natural salts contain brine in grain boundaries in the form of inclusions and films. They're connected to varying degrees, but they are present in every natural salt. And only a tiny amount of water, for example, for this natural salt from Germany, just 100 parts per million of water, if it's present at grain boundaries, if the grain size is 5 millimeters, that implies a film thickness of about 300 nanometers. A 300 nanometer film of brine has the properties of liquid brine. Okay, there's nothing weird about it. It's a liquid, so it will support very, very rapid diffusion. And so we immediately, from our knowledge of these kind of processes, the role of water and other rock materials, we realized that creep by the mechanism of pressure solution must be possible in these materials. It ought to be possible if the fluid is connected. Pressure solution is a process whereby under the action of dialectic stress at the grain scale, matter will dissolve at high stress interfaces, diffuse through the boundaries and precipitate at low stress interfaces in a manner very similar to high temperature diffusion creep controlled by vacancies, but when water is present, the diffusion occurs through this fluid film. We thought this must be possible. We also thought that what we call fluid-assisted grain boundary migration, this was Janos's absolute speciality, pressure solution was a bit more my stuff, okay, that this process should be possible as well. Well, what is this? This is, imagine one of these grain boundaries containing fluids, and I've just simplified that here to a film of fluid, and many of these boundaries do contain films. Then, if you have a grain which has lots of dislocations and another grain which has low dislocation density, there's a difference in the free energy of those, and the high energy grain will dissolve, precipitate on the low energy grain, so mass will be transported, the boundary will migrate into, so that the low energy grain will eat up the high energy deformed grain, and you'll get new grains growing, changing the microstructures, completely reworking the microstructure. Now, when we started out with this work, this phenomenon was unknown in salt. Okay? It had never been seen. People said, well, this can't happen because saturated solution. Yeah, but saturated with respect to what? This grain and that grain, right? So, the very first evidence came from some experiments that Janos and I did together. These were stress relaxation experiments on natural rock salt, and we conducted them at 150 degrees And we deformed the samples log deviatoric stress against minus log strain rate. We deformed them rapidly by plastic deformation processes, and then we arrested the motion of the loading piston, and we found some kind of startling results. If they were triaxial tests, if we conducted these tests at a high confining pressure, 10 MPa, it's a very old plot, but I think you can just see 10 MPa, what we saw was that during stress relaxation, first there was this response here which reflects the work hardened properties of the rapidly deformed salt, and then at a certain point, whoosh, the stress just falls off, and you see basically an approach to a linear relation, N is 1, right? A linear relation between the differential stress and the strain rate in the log-log plot. It has a slope of 1, that means there's a linear relationship. So we saw this transition towards something which matched up with our ideas about this pressure solution process, linear viscous grade. If we perform those experiments at much lower confining pressure, just 2.5 MPa, it didn't happen. And our interpretation of this was, going to have to be based on the microstructure. So we looked at the microstructure. This micrograph was taken by Ineris. I did these experiments. And what we found was that normally when you deform rock salt at these kind of stresses, you get, this is a grain boundary, here's 2 old grains, very, very strongly deformed, full of substructure which is caused by dislocation. Okay, crystal plastic deformation. But what we found was the entire sample was getting eaten up by these new crystals, which were almost free of dislocation. So inside the sample was recrystallizing and reducing the grain size. Okay? Reducing the grain size from 5 and 6 millimeters to 1 or 2 or 3 millimeters. And because this pressure solution process is strongly dependent on grain size, our interpretation was, okay, what's happening here is that we're getting recrystallization, reduces the grain size, there's a mechanism switch to pressure solution. And why then don't we get that at low confining pressure? Well, the reason was actually, our interpretation of it, and the reason was quite simple. Up here, the samples were dilating quite significantly. Well, what will happen if you dilate these boundaries containing fluid? The fluid will vaporize and the process will stop, so you won't get it. And that already, we published that, and nobody believed it. People said, no, we've never seen this. With the exception of Philippe and 1 or 2 people in the United States, but by and large, the community said, no, we've never seen this. But what is truly incredible? Nobody ever looked. So up until that point, people had not looked at the microstructure in a way that would have revealed these. They just said, we don't see any change. No, you don't see any change unless you're really experienced. You don't see any change unless you look at sections and look at the microstructure. People didn't believe it, with the exception of Pierre and his team. Okay? So, let me tell you now a little bit more, and Alex, you must keep your eye on the clock for me here, because I feel myself getting into a wave, so I could go on forever.
15, 20 minutes?
Yeah. I shall do my best. Okay, so let me tell you a little bit about the theory of pressure solution and how we took this further. All right, so this is a single grain inside a polycrystalline material like salt, and imagine now that the grain boundaries contain fluid in some sort of connected channel network, or possibly in some kind of film. It might be an adsorbed film, it might be a film of a free fluid film locally present. When you apply differential stress, let's say sigma 1, sigma 3, you increase the solubility of material here compared with here. You increase the chemical potential, and this increasing chemical potential of atoms at the highly stressed surface, ions at the highly stressed surfaces, leads to dissolution in the fluid, diffusion through the fluid, and precipitation. And that mass transfer causes friction. And you can show that in a material like salt, that those serial processes, dissolution, diffusion, precipitation, the slow process there has to be diffusion, because the reaction of dissolution and precipitation, sodium chloride, is extremely, extremely fast. It's so fast it can't be measured. Okay? So diffusion is expected to control the rate, and on the basis of that, of course, if you know the stress, you know the difference in potential, solubility, you know Fick's law for diffusion, you can obtain an expression for the rate of transport and the rate of creep. And that basically, that model tells us that the axial strain rate would be linearly related to the applied stress, inversely proportional to the grain size, the grain diameter cubed. Okay, then we have the gas constant, absolute temperature, the molar volume of the solid, and this is a geometric constant. And this term, this is what determines the absolute rate of the process. This is the diffusion coefficient in the fluid film, the concentration of dissolved solid in the fluid film, the average concentration, and this is the thickness, the average thickness of the fluid film. So this term, this is a kinetic parameter. It controls, it's if you like the grain boundary diffusivity. It controls the rate of transport. If you know that, you know the rate of this process. Okay, now that was a theory. And what I figured out at that time was, okay, well, I put in a few numbers here, and it predicted that this strain rate would be very, very low, just far too low to measure in a lab experiment on natural salt. It predicted the strain rates of 10 to minus 12, or something like that, just too slow to measure. So, you know, for natural salt grain size, this is just very, very slow, outside the range of normal lab experiments. What could we do about it? And so this is what we started to do. We thought about compaction, okay? Because in a compaction experiment, you can control the grain size, make it very, very fine, and the effect of the porosity will increase the stress at the grain contacts, decrease the diffusion distance, so the process will be dramatically accelerated in a compaction experiment if you use very fine grained salt and compact it wet. So that was the idea. Exactly the same theory applies to this. So the compaction strain rate of a porous material like this follows exactly the same compaction creep law, volumetric creep law. And here's this kinetic parameter. Here's the stress. This is the effective stress, the implied stress minus fluid pressure. Here's the grain size. Okay. The only difference compared with dense salt is this function here, which is a geometric function describing how the process slows down as it densifies due to the increase in the area of the grain process. Okay? So this, if you have high porosity, the process will be very fast, and if you have small grain size, the process will be very fast. So by compacting a highly porous aggregate with a fine controlled grain size, we should be able to see if this process occurs in rock salt. At that time, nobody knew if it occurs in rock salt or not. Okay? So what we did was a whole bunch of compaction experiments on salt. Fine-grained salt, you see here grain size of about 200 micrometers, and we measured volumetric strain with time for different applied stresses, saturating the pores with brine, and we saw this kind of behavior. Dry samples did absolutely nothing. Okay? It just didn't creep at all, compared with the rates at which we were measuring with this wet stuff. And you see here, there's a clear stress dependence. So what we did was we had fixed volumetric strains, which was the same as a fixed porosity, because we all started with the same initial porosity for all the samples. Fixed strain would then be a fixed porosity. At fixed strains, we measured the rates, and we determined how the strain rates at fixed amounts of strain, fixed porosity, how those strains depend on stress and grain size. And this is what we found. Okay, volumetric strain rate against stress, a log plot. And you see here that all of these data measured at different amounts of strain had a slope close to 1, much less than 5, which is associated with dislocation processes. Close to 1, and the grain size dependence, so now we have the volumetric strain rate against log grain size. And you see here measured, if you measure how the strain rate depends on grain size at a fixed strain, you see these are the data sets, and they have a slope very close to -3, which is completely consistent with this theoretical norm. We also measured the temperature dependence. I don't have time to show you that data. The upshot is we found that this compacted salt, it exhibited behavior which was very, very closely consistent with this theoretical model. Linear stress dependence, inverse cube grain size dependence. What we did then was we fitted this model to the experimental data to determine this DCS parameter, the diffusion coefficient. Okay? And we determined its temperature dependence, so it has a value of about 10 to the minus 19 meters squared at 20 degrees C, and it has an activation energy of about 24, 25 kilojoules per mole. The microstructure told us for sure pressure solution was occurring. Here you see these grains dissolving into each other and precipitating new crystals in the pores. So pressure solution was absolutely confirmed as a mechanism. And we looked in the grain boundaries and we could see the grain boundaries were full of all these rough structures filled with. Was that bell the end of my talk? Or not? Okay, great. So,
12 minutes.
So, thank you. So, what did we do then? Well, what we did then was the following. We measured the value of this parameter DCS. Okay? We knew its temperature dependence. So, we could insert it into the theoretical relation for deviatory creep. We'd obtained it from experiments on compaction creep, that we could insert it into the equation for deviatory creep to predict the rate of deviatory creep in dense rock salt. And the very first thing that we did then was to compare those predictions with measurements of deviatory creep made in triaxial compression tests, also on fine synthetic salt. That was the first step, because that would be the only thing that would be fast enough to do in a reasonable time. Okay? So these are the data. This is log stress minus log strain rate. And these are Janos's experiments. The points are the data points. And you see here, this is for 80 micrometer grain size dense salt containing 1% brine. And this one here is 200 micrometers room temperature, 200 micrometers grain size. This is 200 micrometers, 50 degrees C. And so those are the black dots and the lines are the experimental data, creep tests on dense synthetic salt, very fine grain. And the bands are the predictions from this model, including the uncertainty that we measured in this kinetic parameter. Okay? And you see it matched up really, really well, including the temperature dependence and the grain size dependence. So at that stage, we were actually really pretty happy that this process definitely goes on in salt. In NaCl, it happens. Still, nobody believed us, because it wasn't real salt, it wasn't natural salt. Okay. This was the microstructure of that very fine-grained material, another micrograph taken by Janos. This was the 80 micrometer material. What you see here, if this is deformed by 15% shortening or something, you don't see grain flattening. So you have relatively equiaxed grains, no dislocation substructure. You find no evidence of dislocations in here. There's no lattice preferred orientation. That tells you it's not dislocation creep, it's diffusion creep. This confirmed, this has to be pressure solution. Okay. Now, in the years after that, when we still nobody believed any of this stuff, I and my students in Utrecht did a lot of work on doing creep experiments at a really microscopic scale, looking at individual contacts to actually understand the fundamentals of this process. So we did a lot of experiments like this where we pressed one crystal of sodium chloride against another crystal of sodium chloride, or against perhaps a calcium fluoride plate or a glass plate, and so on. And we did this in the presence of brine, and we measured creep at this tiny scale. And we found if the samples were dry, then there was an initial bit of plastic deformation. You can see the crystal deformed, plastic, you can see it under the microscope. If we added brine, whoosh, off it went. It started to deform, it started to creep. And we measured these creep curves, these tiny little assemblies of just a few hundred micrometers in dimension. And here you can see, looking down on the corner of a cubic sodium chloride crystal dissolving away against a calcium fluoride plate. And sodium chloride and calcium fluoride are transparent to infrared radiation, so we could send an infrared beam through the contact in an infrared microscope and scan the absorption spectrum. And that's what this shows here. The contour maps here show the thickness of the brine film present in some rough structure. It told us that on average, this dissolving interface was a rough, dynamically evolving structure with a thickness of about 100 nanometers. And we measured again from these experiments this quantity DCS at the top here, and again we found it to be around 10 to the minus 19. In some experiments it was a bit higher, in some experiments it was a bit lower, but basically it's that order of magnitude. So that gave us a basis to predict pressure solution in natural salt. We were at that point really confident we could do that. And so what we did was we took dislocation creep laws for salt determined in regular lab experiments at rapid strain rates, and we predicted what would happen at lower strain rates. So here you see log stress, log strain rate. Here this is dislocation creep behavior 20, 80, 140 degrees for a whole bunch of showing a range of different salts, but data published by Lavasik and Zoik, 1986. These experiments deformation occurred very definitely by dislocation mechanisms. And our model, here it is with our DCS, predicted a transition to pressure solution, indeed, at a strain rate of around 10 to the minus 12 for a grain size of 10 millimeters. When we first did this, nobody measured deformation of salt at those rates under confined conditions, okay? Nobody measured it under confined conditions, which meant if they'd gone to higher temperatures, any water would have been driven off. Okay? So this is what we predicted, and here's the plot on the right shows a similar sort of thing. We took the creep law from the BGR in Germany, and we combined that with our predictions for say 5 millimeters and 3 millimeters. It predicts a transition from dislocation creep to diffusion creep. At strain rates of around 10 to the minus 12, perhaps a little bit past 10 to the minus 11 for finer grain material. Nobody believed us. Okay? So, very, very few believed these predictions were relevant to natural salt because they said it's synthetic salt, it's fine grain, you put water in it, it's not the real thing. And there was a distinct feeling of many people did not want to know this because it changed the picture. So few in the salt community really believed our predictions were relevant to natural salt, with the notable exception of Pierre and his team. Pierre welcomed us, he believed us, he wanted to know, and from about 2014, Pierre decided, I'm going to find out. That's what he decided, all right? And he started doing these wonderful experiments in the mines, and he also growing feeling that some creep was going faster at these low stresses from cavity measurements and so on. He wanted to know, and so he started these wonderful experiments together with Hakim and Benoît and Laura and many others were involved in this whole series of experiments with on and on and on under SMRI funding. And Hakim and Lara are going to tell you all about that later, so I'm going to go straight to the results. So in 2019, Pierre and his co-authors published a paper which showed these creep data. So this is creep rate in units of per day against deviatoric stress, logarithmic scale. And here are data from the YMOS team, which is in the dislocation creep field. And what Pierre found in these extremely long-term, very, very low stress, unconfined creep tests at very, very low stresses in the mines was very clear evidence for a transition from power law creep, which then is about 5, to linear viscous flow, essentially, which then is 1. So linear creep at stresses below about 3 MPa. So Pierre's experiment confirmed linear creep because of low deviatoric stress. His data showed that creep was fastest in the finest grain samples, and slowest in the coarser grain samples. Samples without water didn't creep, deliberately dry ones didn't creep, single crystals didn't creep. Okay, the rates of creep that Pierre and his team measured were really quite similar to what we predicted for those samples. Many of them had a grain size of about 4 millimeters. Okay, so it confirmed this picture, despite the fact that the grain size, of course, was 100 times bigger than what we used. Okay, I have to round up now, so I will go on and very quickly say this. Then finally, people believe this. Okay, that was 2019. That was 1 year after the 2018 SaltNet 9 conference, and it completely changed the picture. So in 2022, SaltNet 10, which was held at our lab in Utrecht, 30% of the papers mentioned this process of pressure solution, mentioned the change and the weakening seen in the salt, and very many of them, about half of those, actually built this behavior into constitutive models and started predicting, taking into account numerical modeling of cavern closure and everything else. So Pierre completely changed the picture. I have lots more I could tell you, but as usual, I've talked far too much, so I'm going to skip right to the end and simply tell you that, go to my conclusions. I should say there is very strong evidence for linear creep in rock salt below 3 to 5 megapascals by pressure solution. We predicted it 35 years ago, knowing then that very little water is needed. It was totally, absolutely not accepted until Pierre's work with his very slow creep test. It changed the game. So this is the present state. I've gone from the past to the present. Linear creep laws are now entering engineering models for caverns. It's important for our field. It has a really big impact on predictions. Much research still needs to be done. One really crucial thing, and perhaps you'd have picked this up, it's really crucial that lab tests avoid dilatancy. Because if you have dilatancy, the grain boundaries open up, the water escapes, and this process doesn't happen. You don't see it. It's also absolutely crucial that we look at the microstructure of lab experiments before and after the test, and we measure the grain size. Okay? And what is also very important, of course, is lots of field and monitoring. Thank you. I'm sorry I went on.
We will continue this session on rock salt mechanics, and the next presentation is given by Hakim GHARBI, who used to work with Pierre over 20 years at least, more than 20 years, and he was closely involved in the development, technical involvement of measuring devices for these slow experimentation. So, well, Hakim is going to provide the details about his work with Pierre.
So, okay, good morning everyone. First of all, I want to thank the organizer for giving me the chance to talk today about these topics. So, grid test. Very early, more than 30 years ago, Pierre Berez had seen the interest of developing grid test under very small load. 25 years ago, I started to work in the lab with the development of a high resolution all silica displacement sensor. It was already in silica. It was in silica because we wanted to overcome the influence of temperature. And it was in collaboration with someone in the EPGP, Institut Physique du Globe de Paris. That was with Pierre-Antoine Blum. And for me, it was a pleasure to work with Pierre. Here you can see him in the great garden of Suzhou in China. He's happy. And it was a pleasure to work with Pierre because there's a great pedagogy, his scientific quality, and for his rhetoric and his British flag, because he was very good. He has this aspect of his personality. So now let's talk about very slow fluid test on some sample from 0.2 to 4.5 MPa loading characterization. And here you can see that this work is a result of the collaboration of several private and public organizations. And above all, funding from the SMRI for 2 research programs. So SMRI, Solution Mining Research Institute. And as you can see, Janos was involved in this program. Exactly. So let me present you the outline. I will start by explaining the context of the study, why we want to do this, perform this test. I will start by talking about after the context. I will continue to explain the difficulties to realize this type of test on the solution provided. I will end up with the result. Detailed discussion and conclusion. So, in this slide you can see here a natural structure in the soil. Oops. It's a salt dome. The hydrostatic pressure around is close to 5 ampere, or less 5 ampere. It's related to the difference of the density of the soil and the density of the salt. You can also see here a cavity, intercell storage, where you can see that it's a cavity used for hydrocarbon and gas storage. And you can see through the years that the volume of the cavity is decreased. All these phenomena are structure are under constant law under 5 ampere. And here you can see a calculation of calculated of deflector stress around the cavity of air compressed storage. This cavity is at 750 meter depth, and you can see that the range of interest around the cavity is from 0 to 5 ampere. So, this slide you can see a figure where there is a compilation of data from respect. Here you can see the dot are the steady state strain rate obtained after a Cube test. So this figure is a strain rate with a function of deflector stress. And what we can see is that all the tests are doing at Cube tests at load more than 5 ampere. Under 5 ampere, we have any test, and all the lines that you see is steady state behavior obtained with Norton Off law based on the experiment obtained after 5 MPa law. So, why in quick tests are not performed in the relevant domain of stress of the lab? Why? I think it's due to the essentially that when we measure the deformation, we have strain, thermal strain that will parasitic. They are parasitic because you will see after, but we research to measure this viscoplastic strain, and we cannot avoid in lab easily temperature fluctuation. So, a little numerical application. Here you can see if we want to measure steady state, real steady state under 1 MPa load, and we will have something close to 10 minus 13 per second steady state strain rate. So during 5 weeks, maybe we will have something like 3 on 10 minus 8 deformation. And if we measure the thermal, if we calculate the thermal strain obtained with 0.01 degrees Celsius, we can see that we obtain a deformation greater than the deformation that we want. So the same can be said of humidity influence, and for summaries, we need an extremely stable temperature and humidity for perform this type of test. Typically, typically 0.01 degree and 0.5% of relative humidity. What was the solution? The idea of Pierre, it was to install the devices inside the mine. And here I will show you some results of devices installed in Altossi. Altossi is in Austria. This is a typical village close to, not so close, but at 1 hour from Salzburg. And you can see that we are far from Paris. And it's a very nice village, sometimes cold in the winter. And here you can see the mine, the entrance of the mine, because the mine is in the mountain. Also, we performed the test in the mine. The devices were installed in a remote end gallery of salt, in the salt mine. And the temperature and humidity, as you can see, are very stable. Here you can see data, measurement of the temperature, concerning the measurement of temperature. As you can see, it's very stable. So, I remember it here, what must be the testing condition for obtaining our result. We must have a temperature fluctuation very low, sensor accuracy very good for measure temperature at this range. And the sample dimension are 70 millimeter in diameter, and in height we have 140 millimeter. Dead weight were used for being sure that the regulation will be perfect. On the range of stress that you can capture with the devices, we can perform tests from 0.2 MPa to 5 MPa. So displacement sensor accuracy of the order of 12.5 nanometer. And for each devices, we have 4 displacement sensors. And here I present you the first devices. As you can see, we have a sample of salt here. around we have 4 displacement sensors who measure the deformation. Here we have a frame balance like a pendulum, where we can will allow us to bottom to load the sample at the bottom. And here I can use second devices. We can perform some test from 1 to 4.5 MPa on load. This is a cantilever system, multiplier force, where we have a fixed air part at the extremity with ground downshore, and we have a free extremity. Now we put the load, the dead weight here, and the sample is attached at this point at the distance from the fixed extremity, so we can get the force. So here you can see the final installation of facilities in the mine with 3 high load testing devices and 5 classical small testing devices. Now I will present you some results. This result was already presented by Pierre and certainly by Benoît during the mini conference, but I will do a review of them. Here you can see one of the main results is, as you can see here, we obtain this type of figure with a strain, between the time. Here you can see we have 5 steps of load on an average on the sample. The test was during 5 years. At the end of each step, we measure the steady state, strain rate, and if you remember this figure, we superimpose different steady state strain rate, the figure. As you can see here, the strain rate are faster than extrapolated from Brice's test by 4 or 5 orders of magnitude. It has been, as we see before, by cyclical followed by Brice. And another result is a cumulative transient creep is large. If we see here, at each step, the transient creep is greater, is larger. Only for the first step we have a difference because we suppose that we crush the irregularity, but not only the irregularity, there are many another, certainly another reason. If we, another result too, it's around the range 0.1 ampere, 3 ampere, so concerning these dots. We have a linear function of the affiliate stress. And here I show you a figure with the data concerning 3 different salts, and you can see that the nonlinear behavior range lays between 3 to 4.5 MPa. 2 other results. We have done some reverse creep. We observed some reverse creep during a test. Reverse creep when we decrease the load, we can see the elastic answer of the sample, and the sample continues to be in expansion way until to go back in a compressive one. So we can see here too that the strain rate is decreasing function of grain size. We use 3 different samples. You can see that they matter, and we observe that the strain rate is correlated with diameter, but the data are too raw to fully confirm one on E power 3 as predicted by SPIERS of the Royal. So now I will have a little word on paying my tribute to Janis. Like I said before, he was involved in this field test. And I will show you a recent result with Cavern Consortium, where we, after a step on we suppose that the steady state was reached, we changed the mode and we decreased the mode. So the stress drop will be the consequence of the stress drop. The sample will be in reverse creep. Like explained here, we have an expansion of the sample after elastic response. And here you could we had a lot of samples, withbending sample. It's a Dutch sample that Joyce was talking about. And for one of these sample, we do anything. Here it's stuff in the mine. We were working inside, so it's only thermal answer. On the other sample, we'll leave the same thing, but after the first step, we change here the load. And when we zoom on the final view of the figure, you can see that we are in a reverse creep, and during few days, and after these few days, in this positive domain, is in compressive mode, we come back to classical creep test with a strain rate lower than before. So I will conclude my presentation. And often Pierre Berès said we are in an unknown world. During 25 years, we obtained many results and many questions found and answered. As you can see, we perform now the test in the range and testing the range. And one further development which by Pierre was to perform keep test at low stress with confining pressure. We are currently working in discussion with Alexander on the rest of it. Thank you.
Thank you very much, Hakim, for your presentation. Would you have questions?
Sure. Yeah, I have a question. Did you check if there were any microseismic events occurring in the mine?
Not in this one, but we have other tests in Nancy, not near Nancy, partially it's some mine too. We have some tests in the mine, and we have some blowout because the excavation in the cavity is done by explosion, by blowout with dynamite. So we catch sometimes, we see clearly that we have the answer of this blowout on the displacement data. It was really interesting. We see a lot of things. I don't talk about physical things that we found.
I had another question.
Yes.
Concerning the effect of the grain size on the creep rate. Were this test performed in the same sample size, specimen size? If it was the same specimen size, it could be an effect of say the number of interfaces between grains much smaller with the large grains than with the small grains. What do you think of that?
Maybe, but we are testing other size for and we will have a result of the different size of sample for seeing if it's very due to the origin of this is a change of the size of It's the size of the sample. So I cannot give you an answer now, but we will have some sample because we test some.
I think we can answer. I mean, what you say, Jacques, is not in contradiction at all. I mean, smaller grains, larger surface area, but this is what you need in solution pressure, solution transfer, diffusional processes happening along the interfaces. That's exactly the point. Now, your question, I think, addresses more the representative volume. The fact that you have to be probably 10 or 20 times larger samples than the grain size, but 70 millimeter samples, and the maximum grain size was 5 millimeters. So I think that we are still kind of representative.
But we will see. We have some sample of the different size now in the mine.
Okay. Thank you very much.
Good afternoon, ladies and gentlemen. I'm very happy to be there for this presentation of one of my research topics on blowout in soil cavern used for underground hydrogen storage. Before starting my presentation, I want to thank the organizing committee of this conference. I see Laura and Benoît and others. For people like me who have to work with the it means a lot. Thank you so much for this opportunity to give us to present. Few words on me. I'm a graduate and graduate from this school. I have a PhD from École Polytechnique. I work here. Started 13 years ago with Pierre Beras in the laboratory, in the solid mechanical laboratory. And since that day, I never stopped collaborating with Pierre Beras. I will have tomorrow the entire day to cry, to commemorate everything. So now I would like to focus on this subject. For my presentation, this is the outline. The first is a general introduction to explain why it's important to know how to calculate blowout, to predict the duration of the blowout, etc. And in the first one, I will try to select two caverns, a real cavern and a generic cavern, and explain why I'm selecting those caverns, and showing for the rest of my presentation which type of thermodynamic property of gas I will use, and the hydrogen potential risk. And after that, I will focus on the underground blowout prediction model that Benoît just presented you. And with this model, I will show you the result of this model for those two sort caverns, a real one and a generic one. And I will show you also some result of the sensitivity analysis of our model on important parameters like well length, if the cavern is shallow or deep, what's the impact of the production diameter, if the diameter of the tubing is small or large, what's happened. On the gas nature, we use hydrogen, methane, or compressed air. And cavern geometrical characteristics is mainly the volume of the cavern, if the cavern is large or small. And last, we will present some idea on the mechanical stability of some caverns to be submitted to a blowout. And at the end, we will talk about the aerial modelization of a blowout, when the gas flow outside the cavern, what's happened, etc. I don't present the video there. A few words on me again. I'm a research scientist at Ineris since 3 years. Ineris is the French National Institute for Environment and Industrial Risk. And in my direction, I'm working with a team dedicated to the numerical computation in rock mechanics, geomechanics. this is some kind of a hot topic in my unit. You have a synchronization of single highs. You have radioactive waste management. We are working up with BUE project on that. This is the blowout modeling I will just show you. And this is the subsidence effect of underground void at the surface. It's important for brine production operator companies. And we also have a kind of hazard monitoring, salt cavern abandonment. In my team, people work a lot with Pierre on this subject before coming because the hot topic of this last year is the underground production of hydrogen. Let's go to the next. I don't have a video. Thank you for Benoît for the video. I just have pictures. This to show you that blowout can be very terrific. It's one of the most feared events in this kind of new technology. I mean the underground hydrogen storage. But we don't have examples. We have 5 caverns in the world operate with hydrogen, but no data. But we have some examples of blowout with natural gas, like Moss Bluff that Benoît just showed you, and the Prudhomme that was present in the last SMRI. In those examples, Moss Bluff and Prudhomme, the gas flow outside the cavern and the well bore is lasts kind of 6 to 7 days, and it's very difficult to manage. Sometimes people try to stop the well. And there is another example here in a tank underground storage salt cavern in Canada. But my presentation is on salt caverns. I put this another example, it's kind of a gas eruption is at the Allison Canyon underground storage site in porous media in the US. That last kind of form of, that's for people who are trying to store hydrogen in porous media. I don't want to calculate the money with this kind of great loss. Okay, so the work I will present is sponsored by the HIPSTER project, just presented by Grégoire. I will just list here. It is kind of a project where we want to install a demonstrator in Utrecht in the Storage site. And Ineris is involved in this project. Then we are doing a lot of study for this project. The main study is the risk analysis because we are the head of the work package dedicated to the environmental assessment and risk assessment. And when we studied the risk, we studied the product hazard, everything about the product inside the facility, because as Grégoire just showed you, we have the underground facility and a surface facility. So you study the product hazard, we study the process and equipment hazard, we study the bibliography, the lesson learned about this type of facility around the world and incident, accident, etc. But we retain that the major hazardous phenomena that can happen in that kind of site are flash fire, jet fire, explosion, burst, and toxic effect. And the other central fear effect can be loss of hydrogen containment, attex formation, overpressure release. Okay, from now, for my modelization, I will select 2 caverns. My first cavern is the EZ53 cavern, used in the HIPSTER project. But I put a warning here because I really want to modelize the very worst case scenario. So I took the cavern, I fulfill the cavern with the entire 83 ton of hydrogen storage, and I simulate the blowout. This is not what will be done in the site. The project will involve only 2 to 3 tons of hydrogen. So the result I will show you is the very, very worst case scenario, not really linked to the project. And because this cavern was very small comparing to the other caverns using to store hydrogen, like as you can see in this slide, so you have a kind of 80,000 cubic meter, but caverns are often 500,000 cubic meters on geometrical volume. I select another cavern I call it cavern 0, like a generic cavern. I want this cavern to be similar to the Clemens Dome storage in the USA, and I will show you the result both in the EZ53 and with this cavern. With this cavern, I did some sensitivity analysis we'll talk about later. So this is another picture on thermodynamic parameters I use in my model. Not to mention that hydrogen is a light gas, extremely flammable gas, incompatible with oxidant. Permeation can be possible through material, fragmentation of metallic material, interaction with the underground environment. Okay. All the model, as we just saw, is already implemented in the local software. We are using this sort of software in Ineris during the Hipster project. And the advantage of the software is that it is fully coupled with thermodynamics and rock mechanics. So we can modelize the blowout and see what is the impact of this blowout on the mechanical stability of the salt caverns. Yeah. So the cavern thermodynamics and the soil mechanic, rock mechanic are calculated simultaneously. This is some house software, etc. So for the blowout modeling, my presentation will be divided. I say that the blowout is kind of an uncontrolled release of the gas, of the store gas, of the pressurized store gas from the cavern to the well and from to the outside when the control of the wellhead fails. So for this modelization exercise, I will present in two parts. The first part is the underground part. I will show you how to use the BRS model developed during my PhD studies with Benoît and Pierre to modelize the blowout, and how this model, I will show you in detail how this model has been developed, has been tested, has been validated for the test. And after that, I will present the work of my colleague at Ineris for the modelization of the area part of the blowout when you have a source of gas flow in the air, in the atmosphere, with atmospheric pressure, what's happened, what is important to calculate, to demonstrate how the gas can be dispersed in the environment, etc. For the next slide, okay, that's my second point on underground blowout prediction model. This is our model. For our model, the main assumption is that the cavern is located somewhere in the rock mass, and we took into account the conduction of the head coming from the head mass, plus the convection that we might just present, and the possible condensation due to the presence of the brine, some brine, the remnant brine up in the lower part of the caverns. And we use a higher assumption that inside the salt caverns, the pressure or the temperature is constant. And these assumptions come from literature for real measurement performed by Andreas Banach in Germany. We can complexify the model, but it's not the subject here because the objective of the model is to predict the blowout duration and to calculate the main thermodynamic properties. Next slide. Okay. This is the energy balance we use in our model. So the energy balance will show that inside the cavern, the internal energy inside the cavern should be in balance with the energy from gas injection, if there is some injection, the head flux from the rock mass with the Fourier law. Nothing working. Okay, no. And the last part is the condensation. Okay. And the last part is the possible condensation inside the current. This is we developed this model during my PhD. It's kind of a PVT modeling that we develop and we can apply with real measurement of caverns. We apply it with some measurement again in Saskatchewan in Canada and in Germany. And this sample model helps to describe pretty well the thermodynamic property of the stored gas inside the soil caverns. When we talk about the blowout, we need to couple the cavern and the well. And this brings us here when we need the state equation for perfect gas to simplify for natural gas or compressed air, and the Van der Waals law for hydrogen. This is in order to define the enthalpy per unit of mass. This is the mass conservation equation from the Kaisen-Chodef. It will be useful to use the energy equation, taking into account the gravity. When we were developing the model, we test the model because we knew that the rate, the velocity rate were very high. We test the model with or without taking into account the gravity acceleration, and at the end it's important to take into account the gravity acceleration. There are also the constitution of positivity of entropy, and that's the energy balance equation. We made a lot of assumption, simplification, because we have the objective that I just told to you, and some boundary condition. The flow is kind of steady state flow with non-adiabatic because the head is coming from the rock mass. We have a circular duct, but we also develop another model with a rectangular duct to apply in a specific case study. So the head losses, about the boundary condition, we at the beginning of blowout, we fix the pressure, the temperature, and the volume of the stored project. And the main assumption of the model is the funnel flow model that Benoît just presented. This means that at the beginning of the blowout, when the wellhead just break, the condition of the limit of at the wellhead, you have the pressure, the gas pressure can be high, and when during the blowout the high pressure is high, we fix that at the beginning of the blowout the velocity could not reach the velocity of sound, and then during the blowout when the pressure drop till coming to the pressure, atmospheric pressure, the new boundary condition is the pressure at the wellhead is equal to the atmospheric pressure. I will show you. So in our result, we will show two situations. What happens during the shock flow and what happens during the normal flow when the pressure at the wellhead is still it begins equal to the atmospheric pressure, but there is still the flow outside coming from the wellbore and the caverns. Okay, we apply this model to the Mosque Bluff, thanks to Benoît, who won his SMRI research project during my PhD, and he just showed you the result. The result was confident with the observed. The blowout lasts 6 to 7 days, and the evolution of pressure temperature was not. It was very coherent, and we also apply this model to a specific case study, kind of a mine in Kansas. You know, where we've abandoned mines. When we plug the mines, the water flow continue and compress the air, and one day suddenly the shore goes outside and the air goes outside. We apply on this, and the result of our model was pretty confident with the observation that the eruption of this well lasts around 10 minutes. Okay. This is about the validation. I will show you now the application of this model, the result of the application of this model to the two caverns I just showed you. I mean the EZ53 salt cavern and a generic cavern, a bigger one. the EZ53 cavern is around 8,000 cubic meters volume, and the generic cavern is 500,000 cubic meters. Okay, this is the EZ53 cavern, and this is the generic caverns with 500,000. So at the very beginning of the blowout, these two figures shows the distribution of the gas pressure and the gas temperature from the cavern top, I mean the casing show depth at casing show depth to the surface. So at the very beginning of the blowout, we have the pressure goes from 15 megapascal to 1.5 megapascal inside the well bore. And we also have the evolution of temperature that goes from 45 degrees Celsius. I told you that at the beginning we fixed the pressure and the temperature. We suppose that these data are known. It's 45 degrees Celsius of temperature to -3 degrees temperature. The interesting thing is here is this effect we observe here. You are inside the well, you are cooling the well, but there is some heat, there is some temperature increase inside the well called the Joule-Thomson effect. Okay. From now, when you will see this and the gold color, this means it's the result of EZ53. And here, I just stopped the presentation. And here, when we see this, is the biggest cavern. And this is the result. I will show both results. I will comment both results. So I was here commenting this evolution of pressure from the underground, from the casing show depth to the surface. The evolution is similar at the very beginning. For the biggest cavern, we goes from 17 megapascal to 1.6 megapascal at the well head, and the temperature we also observe the Joule-Thomson effect here. Next slide. This is now the evolution. These two figures shows the evolution of the gas pressure and the temperature during the blowout. As you can see, the blowout in EZ53 in a very worst case scenario can last 3 to 4 hours. And this is not the case of our project, because in our project we will store only 2 to 3 tons of hydrogen. But in my case, I fulfill the sub-cavern with 83 tons of hydrogen. So this is the first result, the duration of the blowout. And you can see that during the shock flow, and at the very start when the velocity are very high, we have a kind of 90% of pressure dropped until the pressure at ground level equals to the atmospheric pressure. This is the shock flow part, and this is the normal part. So you have a pressure drop of 90%. And as Benoît just presented, the minimum temperature observed during the blowout can be very, very negative. Here you have -66 degrees Celsius. I plot in the black cube the evolution of hydrogen temperature at cavern top, and here in gray cube the evolution of hydrogen temperature at ground level. So at ground level you have this. You can find the first cube I just showed you from 15 megapascal to 1.5 megapascal, and then there's the evolution in the time. This is for the EZ53 cavern, and this is for the biggest generic cavern 0. We have with a bigger cavern, you have more 94% of pressure drop during the shock flow until the pressure at ground level equals to the atmospheric pressure, but there's still flow of hydrogen outside the cavern and the well. And here you have minimum temperature around. With the biggest cavern, you don't have this the -66 degrees. You have less, -44 degrees Celsius. So next slide. And here, this slide shows the evolution of the gas density or mass, the evolution of mass as a function of time during the blowout, and the evolution of gas velocity. You can see that in hydrogen, it's different from natural gas. The velocity can be very, very high. We are around 1,200 meters per second, etc. Go to the next. This is the next for the biggest caverns. And we perform some parametric sensitivity analysis with the biggest cavern, 500,000 cubic meters. And this, I can comment just one or two. Here is the result of the sensitivity analysis. Here, these four figures show just only the evolution of gas temperature during the blowout in the biggest cavern. In the biggest cavern, in the bigger cavern, in the 500,000 cubic meters or caverns, the blowout lasts not 2 to 3 hours but 7 to 8 days. And you can see the salt cavern having a small volume are emptied more quickly. You can see here in the cavern volume, we have 1, 2, 3. The first volume is 100,000 cubic meters, 500,000 cubic meters, and 1 million cubic meters. We also, the fastest blowout is that of the salt cavern filled with hydrogen, because hydrogen viscosity is smaller than natural gas viscosity. And we perform all this. I don't have time to go deep, but I can stop here when I plot the distribution of the temperature from the cavern casing show to the surface. As you can see, this is the parameters which varies here is the well length. So we have here a shallow cavern, a cavern at 1,000 meter depth, and a cavern at 1,500 meter depth. And you can see that in this shallow cavern, you don't have the Joule-Thomson effect at all. You don't have this because it is too near the surface. And I just show you our models, the model developed by Benoît and I when I was a PhD student. In my PhD, we used to apply it on gas, natural gas. In the Hipster project, I applied it in hydrogen with some modification. And what about the mechanical stability of kind of cavern? That's for the mechanical stability, we selected the Munson-Danson creep law with the main phenomena, creep, steady state creep and transient behavior creep. And thanks to Benoît who fit for our project a trade with the Hugo test, the parameters, the set of parameters used for the Munson-Danson model. And I wanted to talk a little bit on mechanical stability criteria. For this kind of problem, we can have these main mechanical stability criteria. The first is the onset of salt dilation. The second is the onset of effective tensile stress as cavern wall. Effective tensile stress means that we calculate all the stress, the distribution of stress, and we took the minimum compressive stress, and we add the maximum compressive stress, and we add sigma max, and we add the cavern pressure, the pressure inside the salt cavern. And on the oversaturation of cavern roof, we have to check on the subsidence, is it limit or not, and the volume loss, as Benoît just showed. But for my presentation, I will just check the onset of salt dilation in low-cost software, and we have a lot of salt dilation criteria implemented in the software, which present in the invariant plan the data to assess as function of the pressure, and we select the respect criteria with a set of parameters that was available, and you can see that after a blowout, there is a zone, this area of dilation around the salt cavern, and now we are working to better understand this area, what really happened, how microfracturation or fracturation develop, what are their length, what are the space, etc. We are still working on that. But let's go to the higher part of the blowout. I don't know if I have 10 minutes or 5. Okay, let's go. I will go fast in this part because my colleagues works. So to model the higher part of blowout, the gas just flow outside the cavern, and we have 2 exercises. The first exercise is to calculate the dispersion of this gas outside in the atmospheric condition, and the second part is to model the kind of hazardous phenomena that can happen. And we select 3 types of phenomena with hydrogen. When you have kind of this house flow hydrogen outside, you can have jet fire, flash fire, and explosion. So we use in Ineris, we use the fast, the traditional fast, and the mixed. Fast is used for 2D numerical computation. That is sufficient for this kind of exercise. And if you want to go deep, you can perform 3D numerical computation with this software. So 2 exercises, calculate the dispersion of the hydrogen cloud, and second one, calculate the distance of effect of each selected dangerous phenomenon. Yes, for the dispersion model, we use the Brouard model. I will not go in very deep in this. And the very important information here is that for about the atmospheric condition, in Ineris we use the Pastis law. We will define 9 classes of the atmospheric condition. It can be very unstable, moderate, unstable, neutral, or stable with some variance. And all this in our model, we have this, we can know when hydrogen has flow from the wellbore and go outside, we can know exactly what is the distance of the dispersion of the clouds. But this is indeed 2D modelization, and we can have another 3D modelization with NIST software with only one condition, atmospheric condition. This is the result of the plume that describe the dispersion of the hydrogen outside the salt cavern. And after this, we want to know what should be the distance of effect of this selected phenomena around the wellbore. So there are some physical description. I don't have time to go deep in this, but we can talk after the presentation. And we calculate for each phenomena the distance for significant lethal effect, or irreversible effect. This is the distance for flash fire. You can see 26 meters. You should not be around 26 meters around the wellbore, 30 meters, 35 meters. This is the distance for the jet fire. It's more. The jet fire is 100 meters from the cavern, or from the wellbore, and the explosion is more. You can have people should not be around half kilometer around the cavern. And with all these 3, I took the maximum and I approached it in a map. You can see this is the irreversible effect. When I used to do this presentation, I used to take the site where I am and put the well and put the distance. But I cannot do it in Polytechnique because it's a military school. I don't want problem. I want to leave. So this is for the jet fire, this is for the flash fire, and this is for an explosion. And this is the end of it. The conclusion. So to conclude, I just show you a model developed by Pierre, Benoît, and I, Geomechanics, that is you apply on the Hipster project that Benoît, that Grégoire just presented you. That really helps to predict the duration of the blowout and the principal parameters of thermodynamic parameters that help to calculate the mechanical stability or stability of the salt cavern. And the other hand, I show you the result for 2 caverns, the E4C salt cavern and a generic cavern with 500,000 cubic meters volume. And we just see that hydrogen is dangerous, invisible. And when coming to the modeling of the higher consequences of the hydrogen, we should focus on the dispersion of hydrogen firstly, know how large is the cloud coming outside from the tube. And there's a lot of theories, there's a lot of studies you can do because you can decide to model the well bore vertically, horizontally, inclined. And you imagine that if the well bore is horizontal, if the conduct is horizontal, there will be more distance, etc. And after knowing how is the direction or how large is the hydrogen cloud outside the sub cavern, we need to consider some dangerous phenomena and calculate distance. Thank you so much.
The idea of my presentation today is to give a kind of very short overview of some of the mechanical, thermal phenomena that are involved when we try to model the salt caverns. Most of the ideas that I will present today are originally from Pierre Derest, and some new ideas maybe from the CCC consortium that Joyce was talking about this morning. You have seen this slide from Joyce this morning. I repeat it just to remember some important idea about salt caverns and rock salt, especially that rock salt has a variety of thermo-hydro-mechanical properties that works on different time and length scales. We have seen this already. And remember that most of the time salt is not pure, it's almost always heterogeneous with different components, different types of impurities. And salt have many very special features. It flows, bends, expands, shrinks, breaks, dissolves, and so on. Many different phenomena. And understanding all these physical processes is important if we'd like to properly model the behavior of salt caverns and cavern fields. In our CCC team, what we promote is a kind of salt cavern life cycles, which start with what we used to call a Ist-Zustand, German word. It means that the kind of initial state that we have to determine before being able to perform numerical computation. And it starts by for any new project, to the selection of a site, to the new drillings, and so to the scanning of cores. And from these cores, these few drillings, you extrapolate what is the structure, the geological structure of the salt dome, for instance. And then you can perform some microstructure analysis on the salt cores. Of course, quick testing. It could be in the lab, as was presented by Brouard. It could be also in the mine, as was presented by Hakim this morning. And then from the testing results, there is a modeling phase to determine kind of micro-scale constitutive laws, and at the end of the day, we have all the parameters we need to be able to perform the numerical computation. And these numerical computations, this is the main topic of my presentation today. What about salt caverns? This is a picture from Cheer, which is in the room here. What you have to be aware of that salt caverns exist since the 40s, more than 70 years old or more, and so it can be considered as a mature technology with more than 2,000 caverns operated worldwide. We are able to store natural gas, we are able to store compressed air, and even there are already existing hydrogen salt caverns. And there are, especially in Europe, but also now in the US, several ongoing projects related to the storage of hydrogen in salt caverns. As you will see, the modeling of salt caverns is a very complex task, because we have to consider both the thermodynamics, which is the behavior of the gas, of the fluid inside the cavern, and also all the rock mechanics. And these two parts have to be, most of the time, to be coupled to be able to perform proper predictions. Just a remark about salt caverns compared to other type of storage above the ground. Typically, salt caverns has a volume between 10,000 to 2 million cubic meters. You can find less or more. And regarding the depth, between 200 and 2,000 meters. It means that you can keep, for instance, hydrogen at a large pressure, typically 200 bars, and so you are able to store a mass of hydrogen which is much, much larger than what you are able to store above the ground. When we start studying salt caverns, it's a kind of a new world because there are so many different types of physical phenomena involved at different scale, from the micro scale to the dome scale. That's very complicated, and there are also some political background. So today I will be only focused on the two first phenomena, maybe the most important, the mechanical phenomena, especially the salt creep, and also some slide about the thermodynamics. But for instance, I just mentioned the dissolution, crystallization of salt into brine, the permeation. It's a strong political issue. Is the salt permeable? Chris said that maybe there is no porosity. I don't know, some people say there is no permeability. Some other people say exactly the contrary. We don't know. There's still ongoing discussion on this topic. Today I'm only focused on the two first. About rock mechanics, you have seen many slides already today on rock mechanics. I would just add some idea. In fact, since early 80s, there were 10 international conferences dedicated only to the mechanical behavior of salt. There was one in '93 organized by Mehdi here at École Polytechnique, and we had one last year in Utrecht organized by Chris. So, and there will be one in the US in the coming months. So it's still a very active topic. Especially because of the nuclear waste disposal, but not only. There are many papers dedicated to salt caverns, not only to nuclear waste. What we can say briefly about the mechanical behavior of salt. Salt, as you have seen, it's highly nonlinear. It could be considered as elastic ductile when considering shock tests, compression tests. It's elastic fragile when tensile tests are considered. And on the long term, rock salt has to be considered as a liquid, as a very viscous liquid, but as a liquid. So it means that at the scale of a cavern, all caverns shrink. It means that on the very long term, all caverns will disappear someday. Here are 3 examples from the literature. These are caverns that were created during the 60s, 70s. For the storage of natural gas. And at that time, the knowledge about the mechanical behavior of salt was not so developed, and so the operators of this cavern experienced very large loss of volume in the early years after the first filling with natural gas. And some example in the US, Equinance, and for example on the right, an example from Gaz de France in Tersa. How we can determine some parameters for the creep of salt at the lab. This is something which is quite simple. We perform what we call a creep test. Basically, it consists in applying 2 stresses, one axial load sigma 1 and one lateral load sigma 3. And with Pierre, we used to call the difference between the two the deviatoric stress. Some other people call it effective stress, but with Pierre, we used to call it this deviatoric stress. And so a quick test, this is the measurement of the strain as a function of time with different phases, an elastic part, a transient part, a steady state part, and in some cases a Fourier creep. As you have seen already, to simplify everything, there are for only the steady state part of the creep 2 different mechanisms. The standard from the past was what we call dislocation creep. It means that can be measured at the lab when the deviatoric stress is, let's say, larger than 4 or 5 MPa. In this regime, the rock salt has a quite non-linear behavior with an exponent of the deviator in the order of 3 to 7. And for the low deviatoric stresses, less than say, 5 MPa, this is a testing that was presented by Chris and Hakim, and we have something which is called pressure solution creep, and which is fairly linear. And the testing are performed mainly in the mines. When we go to the upscaling to determine macro laws that can be used in numerical software, there are, let's say, there are many in the literature, but there are 3 main families that you can find, and it depends mainly on the location of the lab which performs the testing. For instance, in France, School of Mines use Lemaitre or Artiel laws. In Germany, this is Luby 2 law, and in the US, mainly a law called Manson-Dawson. Lemaitre law is mainly a transient law, and the 2 others are also an additional steady state part of the mechanic. The reverse script, you have seen this from Hakim this morning. This is something that is very special with rock salt. You have a load on the sample for a few weeks, few months, and then you just remove some part of the load, keeping some load on the sample, and it's very counterintuitive that for a while you get an increase of the size of the sample. So it looks like the sample is providing some energy to the system, which is a bit counterintuitive. And this is a topic on which Pierre was still working in the last months. He was looking for a modified version of the Manson-Dawson law that is thermodynamically consistent, and it was not so easy. I remember he was thinking of this night and day for months, and unfortunately it was not really implemented yet in a code. I think we hope to be able to do this in the coming months, but it was not yet implemented. But it's a nice way to complete the Manson-Dawson law with this mechanism that has been observed both with testing in the mine, but also with caverns during integrity testing. Something which is more philosophical, maybe here. This is about the workflow for the determination of 3 parameters. The standard workflow that has been done for decades is to get some cores and perform tests in the lab with deviatoric stress from 4-5 MPa to technically 20 MPa. And from this testing to adjust the parameters of the treat flow you selected. It works fine, but there are a couple of flaws with this method. First is that most of times these testing are not very long. Typically, one step is 1 month, maximum 2 months, and very often at the end of a step, you don't reach fully the steady state. You still have a transient component, so it's very difficult from this relatively short testing to extrapolate the steady state part of the free flow. What Pierre was promoting, we always try to promote field testing. We always try to promote a way to check the model from field evidence. And this is 2 types of testing we have done. On the left, you have what we call outflow test. This is a very simple test. You have a cavern that has been created, node 1 or new one is filled with brine, for instance, and we just let the wellhead open. In that way, we keep the cavern pressure constant, just the weight of the brine column, and we measure the outflow because the cavern shrinks, so you have an outflow of brine, and we measure this during a few weeks, a few months. We have done this in many occasions with Pierre. And so it's a way to calibrate the creep, because the outflow is mainly due to creep. And there are also some other effects I will describe later, but this is the main effect. On the right, you see something which is similar. The wellhead is shut in, so you just observe the increase of pressure, which is due mainly to creep, and pressure increase is related to creep closure through the cavern compressibility that was presented before. Thermodynamics. Pierre was working on the thermodynamics of caverns at the end of the 70s. He was the first to publish a paper on the evolution of the cavern brine temperature as a function of time. The idea that was that during the leaching we use cold water that comes from the ground, and we dissolve rock salt, which is at a higher temperature because the temperature typically is, for instance, 50 Celsius at 1,000 meter depth. And the transit time of water in the caverns during this leaching period is relatively short, typically a few weeks. It means that at the end of the leaching, the cavern brine, the brine in the cavern is always cooler, smaller, temperature is smaller than the rock mass. And before the first gas filling, the brine inside the cavern is stay idle, and it takes some time to resorb the initial gap in temperature. This is a measurement we made in the EZ53 cavern that was just presented by Grégoire just before. This cavern, small cavern, 8,000 cubic meters, was leached out in 82, 40 years ago. And at the end of leaching, the temperature was 26.5 Celsius. And there was a measurement of the cavern temperature during a few months, 1 year approximately, and you see that after 300 days, the temperature in this very small cavern didn't reach the final temperature, which is natural temperature of the rock at this day, which is 45 Celsius. Measurement was made in 82, some in 83, and we had the opportunity to perform a test in 96. And in 96, we just checked that the cavern was at thermal equilibrium, but it was long after the creation of this cavern. Some important points that with salt caverns, there is always free convection, natural free convection. It is due to the fact that there is a gradient of temperature in the rock salt, vertical gradient, not so large, typically 1.6 Celsius for 100 meters. It's small, but it's large enough to trigger convection cell. In the EZ53 cavern, you see that you have 3 different cells that mix the brine, and means that you have almost the same temperature in all the caverns. Pierre was looking at to determine some kind of rule of thumb to calculate this evolution of brine temperature. So I just don't want to describe this question, but you just have to write the diffusion equation, the convection input, and some boundary equation with dimensionless variables. You can determine what is the relative volume rate as a function of time for the brine. What is important to remember that most of the time this is a very slow process. The larger the cavern, the slower the temperature increase. And Pierre defined the so-called characteristic time, which is the volume of the cavern to the power 2/3 divided by 4 times the thermal diffusivity of rock salt. It means that for the small EZ53 cavern, this is the characteristic time is 1 year, but for a cavern which is a typical natural gas cavern, 500,000 cubic meters, this characteristic time is 16 years. So it means that for a big cavern that is made for brine production with a few million cubic meters, the time it needs to equilibrate the temperature, it's a few decades. Also, at the end of last 2001, Pierre was working on the role of the water vapor, the water content of the gas. and he was looking on the effect of heat exchange between the gas and the brine. When the cavern initially is leached out, it's filled with brine, and then it is first filled with gas. And if the cavern gas rests for a while, there is the vapor is the gas is saturated with the water vapor which originates from the brine side. And what happens is that during the following pressure cycle, injection, withdrawal of gas, from some period of time the gas is oversaturated, and some other period it's undersaturated with the water vapor. This has been observed through the measurement of the temperature both of the gas and of the brine. This is a paper that was made was published last year. And Pierre was able to explain that the observed decrease of brine temperature is due to the fact that at the lower section of the cavern there is no convection. There is convection only in this case in the upper part of the cavern. To be more precise, there is a kind of asymmetrical process. We have to distinguish between gas withdrawals and gas injections. During gas withdrawals, there is a pressure and temperature drop in the cavern. The gas is oversaturated with the vapor condensation that takes place. And so, in some cases, it can rain or even snow in the cavern. And some latent heat is evenly withdrawn from the whole cavern. On the contrary, during gas injection, there is an increase of pressure and temperature, and the gas is undersaturated with the vapor. And so, in that case, the water vaporizes at the gas-brine interface. And latent heat is provided to brine, brine to gas in the case, pressure. So, the two different processes, and these two processes are different, so this is really asymmetrical. This is the equation that comes with all these processes. I don't want to describe it, but it was written by Pierre, taking into account all the former phenomena described. When we look at the stability of a cavern, of course we have to be able to model the thermodynamics, including brine and the gas. There are convection cells in many cases, and as you have seen, the humidity, the water content in the gas plays a role. When we are dealing with compressor storage, with hydrogen cavern, we are frequently we are speaking about frequent cycling. Frequent cycling, it means that we are not speaking about seasonal cycling, but cycling every 3 months, every month. Some people are talking about daily cycling. In that case, we can anticipate to have large variation of the cavern temperature, and this variation of temperature can trigger additional thermal stresses. The order of magnitude is that any change of the temperature in the cavern by 1 Celsius can trigger an additional stresses at the cavern wall by 1 MPa. And you have to be aware that the tensile strength of salt is relatively low compared to other rocks, in the order of, let's say, 1.5 to 2 MPa. And so, in some cases, there is a possible creation of fractures. This is a difficult topic, the onset of fractures, the development of fractures. What we have seen that probably most of the time this fracture will be oriented perpendicularly to the cavern, perpendicular to the cavern. Another mechanism to damage the cavern, this is what we use to call the dilation or dilatancy. This is something that can appear at low pressure. Dilation is a kind of irreversible increase in the salt volumetric strain. This is something that can occur under certain compressive stress states. And so it triggers some micro fracturing, some increase in the permeability of the rock, and a reduction in its strength. In the literature, there are many criteria to describe this onset of dilation, which Pierre we used to consider the one from degrees from respect in the US, that takes into account the extensive and compressive state of stress. For more than 2 decades now, all the studies, modeling we made with Pierre were input in a software that was developed, software called Locas. At the beginning, it was just a few lines of code, and now it's more than 1 million lines of code. It's a kind of monster, and it's made for the modeling of any type of caverns, and also for the modeling of the cavern field. Just to show you some screenshots just quickly, this is, for instance, a cavern field with different caverns, and we were looking at the design of the caverns. With a quite complex geology. This is an example of a mesh, and an example of a vertical cross-section. You can see that it is a soil dome with different formation, quite a complex structure. Something more simple, I will provide you today with an example of a simple 2D computation with a nitrogen cavern. Was a small cavern to 267,000 cubic meters. You have hydrogen in green and brine at the center blue, and consider the depth between 650 and 800 meters. So something which is quite realistic. And we just make a simple modeling of 10 seasonal cycles. From the maximum to the minimum pressure, something which is relatively simple. An example of output we have from the model is on the left here, the loss of volume as a function of time. You can see in this example that the loss of volume, the rate is 0.1% per year on the long term, which is relatively low, but it's because the cavern is relatively shallow. On the right, you have the evolution of both brine and temperature. Also, we are able to calculate all the developed energies and powers, energy that are related to the compression, expansion of the gas, to the variation of enthalpy, internal energy, blah, 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 all these thermodynamical properties. If we look at the stability, this is an example of what's going on, for instance, at the minimum pressure after 10 years of cycling. And we have drawn a contours of the effective stress. And what we call effective stress, this is the sum of the least compressive principal stress plus the cavern gas pressure. And in all the area that is colored magenta here, the salt is damaged because the effective stress is larger than the tensile strength of salt. So it's likely that in this case, for such a shape of the cavern, some blocks will fall down. Worst case scenario, a blowout. This is the worst case because all the gas flows are fused in a few hours in a few days. An example from Texas, from natural gas cavern in Texas in the left, and another natural gas cavern in Canada more recently. And all the mechanism of the way the blowout can be calculated will be described by Hippolyte just after me. I just would like to just make a few comments on this for hydrogen cavern. Maybe you can lose the caverns during a blowout, but you can also use a lot of money, because if you consider only the value of the hydrogen in the cavern, even with a relatively low price of the green hydrogen, $5 per kilogram, at 200 bars, 50 celsius, blah, 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 it's dozens of millions of dollars, just the value of the hydrogen in the cavern. For the modeling, what is very fascinating with modeling of blowout in a cavern that you cannot determine in advance what will be the duration of the blowout. It's a result of the coupling calculation between the rock mechanics and the thermodynamics. And so you need a software that is able to do just two computations at the same time. That's why we developed this in Locas. And this will be described by Hippolyte, but the main important things to remember is that during a blowout, at the beginning of the blowout, the gas that escapes from the wellhead is escaping at the velocity of sound. And the velocity of sound, in the case of hydrogen, it's very large, something like 1,200 meters per second. And so the first phase of the blowout is called the shock flow, and after a few hours, few days, depending on the case, the size of the cavern, the size of the casing of the wellbore, we have a following phase of the blowout, which is called normal flow. An example, I made just a simple calculation for using the former hydrogen cavern, and I just simulate the blowout. And you see that the duration is something like 19 hours. During something maybe like 10 hours, the gas is escaping at the velocity of sound. And what is important to remember is that the temperature on the right, you have the wellhead temperature on the top right here, and the cavern temperature at the bottom right. They are going very low, something like minus 14 Celsius in the cavern. Oh, there is a mistake. It's in the cavern at the bottom right, and minus 56 at the wellhead. So that's something which could be quite counterintuitive. This is the same for natural gas. We get some very low temperature, even if there is a flame, visible flame in the case of natural gas, but invisible flame in the case of hydrogen. There is a flame, probably a lot of heat, but you can get some ice at the wellhead. In the case of Moss Bluff natural gas blowout, it was funny because we were able to prove that between the start and the end of the blowout, the water in the vapor goes from a gaseous form to a solid form, like this. So it was snowing in the cavern. The first time gets snow in Texas in August. So just my last slide. Some conclusions. You have seen that the proper modeling of salt caverns requires both fluid thermodynamics and rock mechanics to be considered and coupled. The mechanical behavior of salt is very complex, still many studies ongoing on this, and quite different from all other rocks. And when we speak about compressor storage, hydrogen storage with frequent cycling, we have to look at the onset of effective tensile stresses that can generate fractures. And for any new project anywhere, what we recommend is a case-by-case study, because the salt is not the same everywhere, and even on a given site, you can have different type of salt. So it's important to look at the nature of the salt at the different scales, from the micro scale to the dome scale, and to be able to take into account the relevant creep flow, the relevant sets of parameters for this creep flow. And we have to take into account the different mechanisms, from pressure solutions, steady state creep, transient creep, reverse creep, and so on. And if possible, as was recommended by SPIERS, if you have the opportunity to take something from the field, to calibrate the data from the field, you have to do. Thank you.
If I understood well, in your slide of the result of calculation for tensile stress, you have also some tensile stresses far from the cavern. Is that it?
Yeah, that's true.
This is
Yes, so we have to distinguish two types of caverns. The caverns that are used for liquid storage. In that case, for brine production cavern or liquid hydrocarbon storage. In that case, what we call effective stress, this is the sum of the least compressive stress plus the pore pressure. But in the case of gas cavern, we don't calculate the pore pressure because we consider that there is no pore pressure at all. So it means that inside the rock, far or a few meters away from the wall, we consider that the gas pressure is transmitted. That's why the criterion is applied using the cavern gas pressure.
Good afternoon, ladies and gentlemen. I would like to present today the Starfish project, especially the acoustic monitoring of the thermo-mechanical test simulating withdrawal in a gas storage salt cavern. The subject is based on the idea of Pierre Berest. It's for that I can present you today this project. And the project was led by Storage, by Grégoire and with some other partners, SPIERS, Salin du Midi, and Ineris. Joël Billiot was, if I can say that, a pillar of this project. And the project was co-founded by the Solution Mining Research Institute, and the main participants are listed just below. With the new kind of storage and the kind of storage using, like the high performance natural gas storage or compressed air energy storage, power to gas, or the hydrogen storage, like for the SPIERS project, the cycles are shorter in time, and that increases the injection weight and so the pressure changes. The temperature can decrease, lower, and the thermal stress are stronger. So the operators, like Storage, needs to take account this new constraint. What is this problem? What is the problem of with this effect, with this thermal effect? The effect of temperature could be a problem during the cooling and the warming associated to the cycles. The temperature in the storage can reach the level of mechanical damaging, as in this case with the fracturing. In this case, you see some fracturing and spalling of the parement of the wall. This effect can generate a radial spreading of the cavity, and finally shorten his life. And it's a big problem for the operators. The main objectives of this project was to highlight the effect of the cooling on the gas storage. It is important to know the localization of this damage, especially depending on the depth. We need to know the type of damage and its growth during the cooling, and if it's possible to have some fatigue process. With the cycle, we need to know if you have a fatigue process with the rock mass. And it was impossible to highlight this process on a sample of rock because it was too small. So, because the scale, when the damage is initiated, so it was necessary to implement this process inside. And the big question was how, because it's not evident. To answer this question, we performed an on-site experiment in Varangéville mine. It's a mine in Lorraine. The experiment was carried out in a specific blind gallery here, a gallery specifically excavated for us. two trench was excavated on the side of the gallery to decrease the stress inside and to improve the tensile cracks. The tensile cracks and the compression stress to tensile cracks occur. Finally, part of the floor has been sanded on the surface of 100 square feet. This is on this surface that School of Mine teams install a cold room to decrease the temperature of the rock. The floor on the side of the cooling room is isolated here to minimize the temperature exchange between the rock salt and the air. Starfish project was a multidisciplinary project with thermo-mechanical simulation to design the in-site experimentation and to understand better the behavior of the salt. About that, you can read the paper. I don't want to speak about this part of the project, but if you want to read the paper of Laura Blanco-Martins or talk with her, she's here. The other main aspect of this project was the experimental monitoring of the temperature with many sensors, 35 I think. Many sensors of temperature and flux was installed in the salt surface and in boreholes. This graph, for example, shows the temperature change with time at different depths and the temperature reached at the end of the cooling. You see the asymptotic decrease of the temperature in the borehole at different depths here on this graphic. But I don't want to describe this part of the project also. Another way to measure the temperature was installed by School of Mine. It is an infrared carousel on the roof here of the cold room. And one of the recomposed picture at minus 15 degrees is here on the cooling. This is the result of the carousel, the infrared carousels. And the other monitoring is the measurement of the deformation rock. It was monitored by gauges sealed in the rock, and four cameras were installed on the roof near the carousel. And the last parameter monitored by in this experiment was the acoustic emission. Here with the Prof. That is what I want to develop today. The ultrasonic device is composed by 10 ultrasonic sensors, 16 ultrasonic sensors. 5, here you have the my rules. Yeah. You have 16 ultrasonic sensors, 5 ultrasonic sensors on the floor, 5 transmitters, and 5 receivers on the floor. And you have also six ultrasonic sensors in the borehole, and in the vertical borehole, in the center of vertical borehole, and 4 sensors in the inclined boreholes to cover all the volume of the experiment. The mechanical coupling of the ultrasonic sensor is provided by a specific salt which melts at 40 degrees. I show you a few pictures of the installation of the sensors inside and outside the cold room. It's my colleagues. For this moment, my colleagues are installing the gauges, the thermic sensor, and the ultrasonic sensor on the probe in the central borehole. This is the central probe with the gauges here and the ultrasonic sensor here. And you have also a temperature sensor on this probe. it's a handcraft probe. This is a view of the final ultrasonic device on the surface of the salt rock mass. You can see the receivers in green and the transmitters in blue on the floor. The cooling fans are on the left side here. It will be important in this in the crack localization on the acoustic activity. You will see later in my presentation. I'm going to show you the main ultrasonic methods that we use for this study. It is quite similar with the study of earthquake. This is the earthquake of Honshu a few years ago. The difference between earthquake and acoustic emission is essentially about the frequency of the event. The difference is about the frequency of the events. For the earthquake, the frequency is below 10 Hz. For the acoustic emission, the frequency is over 10,000 Hz. The first method is the acoustic emission localization. The objectives of this method is to localize precisely the acoustic emission. This method is based on the arrival time, picking on an aversion of this time with two probabilistic algorithms. The accuracy of the localization increases with the number of sensors used in the algorithm. For example, you can follow the accuracy here. This is the ellipsoid of error of the localization. On this localization map with the plan view on the top and the sectional view on the bottom. With only one sensor, the localization, as you see, is poor. With two sensors, it is better, and even better with three sensors and four sensors. You see the principle of this method. In this study, we use all the 11 receivers sensors to process the event localization to improve the results. We adjusted the method with the theoretical localization of the 5 pulses on the surface. We pulse on the 5 transmitter on the surface. With the better algorithm on an optimum velocity field, the average of the uncertainty is around 2.5 centimeters, and it is largely sufficient for the study. After the localization, we need to know the magnitude of the acoustic emission, like for the earthquake. For that, we use an iron ball. Here you have an iron ball that we drop at different height, from 5 centimeters to 1 meter, and we recorded the different signals and calculated the energy at the sensor. A simple equation here links the energy at the source with the energy at the sensor, and the main parameter is the distance between the impact of the iron ball on the floor and with the sensor. After that, we compare the potential energy with the acoustic energy and minimize the difference. And the results are on this graph. The results are on this graph with the height of the drop ball here, and the energy at the source on the left. The difference is minimal with our parameters. We chose exactly the good parameters, and so this calibration is consistent with our goals. The second step of this method is to calculate the magnitude. This method is based on the Gutenberg-Richter relation from the energy at the source. So the result is a scale of magnitude here for each kind of events, pulses, balls, and after that we will see the acoustic emission. For the pulses, it's between minus 7.6 to minus 5.2, and for the drop ball it's minus 5.1 to minus 3.8. For the memory, the magnitude of the earthquake is between 3 and 8 on the same scale, the same Gutenberg Richter scale. So, thanks to these two methods, we performed the cooling of the rock mass 4 times. Not exactly 4 times, 1 time more at the end. It was possible to decrease to minus 27, so we did. We decreased the temperature from the natural level in the mine, 50 degrees, around 50 degrees, to the fixed level, minus 8 degrees and 27 degrees only for the last and fourth cooling. The typical duration the typical duration of the cooling was 28 days to record the maximum of the mechanical changes in the rock mass. The warming duration was variable because of the mine access. It was not possible to access every day to the mine. And finally, the duration of all cycles was around 1 year. The starfish experiment was around 1 year. This is the first result of this experiment. That is the acoustic activity or the number of acoustic emissions. You have the time below and the number of events on the vertical axis for the 4 coolings. The number of acoustic emission is over 20,000 for the cooling 1. This is the cooling 1 here, cooling 2, cooling 4, and cooling 3. The majority of the acoustic emission occurs at the beginning of the cooling during a few minutes. After this rate decrease quickly, very quickly, and gradually during all time of the cooling as an asymptotic curve. More in detail, the acoustic activity decrease also from cooling to the next one, following a negative exponential way. So the maximum activity is on the first cooling and decrease with the other cooling. The magnitude of the acoustic emission is from minus 8 to minus 3, and cover the magnitude of the pulse on the ball drop. It was a change for us. The majority of them is from minus 6 to minus 4. The most important remark in this graph about the magnitude is about the difference between the cooling 1 in blue here and the next cooling. The magnitude of the acoustic emission of the cooling 1 are clearly higher than for the other cooling, like for the number of the acoustic emission. This difference of magnitude is probably due to the initial state of the rock mass. For the first cooling, the rock is undamaged and can store a maximum of energy and release many and strong acoustic emission. For the next cooling, the rock is already damaged and it is harder to store some stress and damage the rock again. Now, I show you a movie of the acoustic emission on a sectional view at different times during the first cooling. During the period of 5 minutes at the beginning and the period of 10 minutes after that, and you can see that the acoustic emission form a swarm here, or a cloud as you want, This cloud is close to the surface at the beginning of the cooling and goes deeper with time. It seems follow the cold front. If you compare the same sectional view for the 4 cooling 1 to cooling 4, you don't see a big difference except for the number of acoustic emission. On this picture you can see the cloud of acoustic emission for the 4 cooling during the first hour. The majority of the acoustic emission are close to the surface, like for the movie. But what you see also is a dip. After 1 hour, for the same picture, the number of acoustic emission is lower, and the acoustic emission are deeper in the rock. You can observe a tilt of the acoustic emission cloud on the left for all the cooling. It is due to the shape of the cooling. In fact, the cooling is asymmetric because the cooling fans are disposed on the left of the cold room and cool better this area, as proved on the infrared picture on the left. You see a difference of temperature between the left and the right of the cooling room. Another way, some other way, you can follow the depth of the acoustic emission with a mobile average. Mobile average window built with 100 acoustic emission in function of time. For the cooling 4, the acoustic emission go for the 4 cooling. For the 4 cooling, the acoustic emission go quickly deeper in the rock for the first days and stay at the same level during the rest of the cooling. The big difference again is for the cooling 1, where the acoustic emission go deeper and sooner. 20 centimeters deeper than the other cooling. The first one is here, and the 3 other cooling are here. Our explanation of that is about the size of the cracks. For the first cooling, we know that the acoustic emission and cracks are bigger compared to the other cooling. The specific radius for the acoustic emission of minus 3.5 is around 15 centimeters. For the other cooling, the acoustic emission are smaller. Yeah. On the cracks also, the specific radius of the biggest acoustic emission in this case is just 6 centimeters. This is the biggest acoustic emission, it's only 6 centimeters. So the influence zone of the big acoustic emission during the first cooling is larger, and finally the cracks go deeper for the first cooling. You can compare these curves with the result of the thermo-mechanical simulation done by Joël. And for this simulation, the maximum gradient stress is 50 centimeters deep, around here. And it is very close to the depth of the maximum acoustic emission after 1 day. After 5 days, here, the acoustic emissions occurs again at the maximum depth or around the maximum gradient stress, meaning around 80 centimeters. This comparison is quite consistent. Finally, you can also compare the depth of the acoustic emission with the post-mortem coring on the left. This is the post-mortem coring along the main crack. The depth of this crack is between the maximum depth of the acoustic emission of the cooling 1 and the other cooling. Those 3 ways to determine the maximum depth of the salt damage are consistent. So we can be confident with this damage zone depth and damage zone damage zone area. The last method we use is a sample method to determine the focus mechanism of the acoustic emission. From the rise time, we see the rise time of the signal. This is the time between the beginning and the maximum of amplitude. This is the rise time. And at first, we tested it with the drop of the ball, the same iron ball here. We assume that the radiation of the drop ball is quite similar with the radiation of the tonsil cracks. And what you see, the rise time is very short, as you see on this picture on the signal. And secondly, to simulate shear cracks, it was very difficult in this case to simulate shear cracks, but we stuck a piece like that, a piece of rock salt on the floor. This is the picture of this piece of rock, and push it up to the crack. The radiation of this acoustic emission is supposed to be similar to the radiation of shear crack in the rock. And the signal is presented on this picture here. And the rise time is longer than for the one of the drop ball. If I come back, you see the difference of the rise time. This is I assume tonsil cracks and shear cracks. And finally, we adjusted our cracking mode selector for the two tests, and the data are on these cracks for the drop ball here and for the shear test here. And the data, it's not it's not many data, but it's sufficient. The drop of the ball is on the left, and the shear cracks test is on the right here. From this selector, it is possible to follow the cracking mode of the acoustic emission during the cooling. We consider the area in between as the mixed cracking mode. In this example, the results are presented for the cooling 2 with the first 100 acoustic emission at the beginning of the cooling. Yeah. Obviously, the cracking mode is a tonsil mode because of stress during thermal contraction. It's logical. But at the end of the cooling, the last 300 acoustic emission here, the cracks are not all occur in the tonsil mode, and you see a clear trend to the shear mode for a few of them. And you see a migration from tonsil mode to shear mode, like that. An explanation of that could be associated with the change of the cracks depth during the cooling. At the beginning of the swarm, the swarm of acoustic emission is close to the surface, and it is easy to change the volume around the crack. Indeed, the tonsil crack need a change in volume. At the end of the cooling, the crack are deeper and confined, so it is harder to change the volume. That favors the shear mode that doesn't need a change in volume. In conclusion of this presentation, we can say that the damage occurs at the very beginning of the cooling, and it is maximum at the beginning. The greatest activity and damage happens at the start of the cooling. After 3 days, the acoustic emission depth is about 90 centimeters. 80 centimeters for the microscopic cracks. And the main mechanism is the tonsil mode, then it trends toward a shear node. This is a picture of the main cracks that you see on the floor of the experiment. Another conclusion is the mean magnitude of acoustic emission, -5, on the characteristic cracks radius of 3 centimeters. It is in the order of the average size of the salt crystal in Varangéville on the surface crazing. This is the radius of the average acoustic emission, and this is one crystal. And another conclusion is that we confirm the selection of the deepest cracks as Cizik and Berest at simulated heat. Here, this is the simulation on the left, and on the right, this is the acoustic emission energy with time, 15 minutes, 30 minutes, and 1 hour. And you can see the same pattern with a few small cracks on the surface and a longer crack with the depth. And finally, the first cooling controls the thermal damage depth. The first cooling is the more important in our experiment. And so for the operators like Storage, it is recommended to begin the operation of new storage with small cycles in terms of time and pressure to minimize the amplitude of the temperature change and so the damage zone. So thank you for your attention. This picture is about all the people who worked about this project. Without Pierre Berest, because he didn't take the picture. And if you have any question.
Thank you, Cyrille. Any question?
If we change the scale from this field scale to the dome scale and the storage scale,
Yeah.
what can we say?
Yeah. The temperature in this experiment was extreme. So I think the storage, the temperature change is below, very below. I think the damage is probably lower, but I think the process will be the same. And I think this experiment was inside, and the scale was not very different with the storage. I think the problem of scale is more between the sample and the insight experiment, more than between this insight experiment with the storage.
Federica PAGLIALUNGA, is that correct? Yes. She is going to speak about the geothermal and induced seismicity.
Thank you. Good afternoon, everyone. I'm Federica. I come from EPFL, and I will show you our work on induced seismicity insight from the laboratory, how fluids can trigger earthquakes. And did this work together with François Passlag, Soumaya Latour, and Marie Violet, and many others collaborators. So I think everyone here knows the potential of geothermal energy as a sustainable and renewable source of energy. So there are different kinds of exploit of this energy production. So the conventional one that usually occurs in volcanical and hydrothermal regions. Of course, this cannot happen everywhere in the Earth crust. So we can also have enhanced geothermal systems. for which we usually increase the permeability of the target formation through stimulation. However, this comes at a cost, and this cost is the risk for induced seismicity. So you can have two kinds of seismicity during these kind of activities. You can have micro earthquakes during the stimulation in the target formation, or you can have what is a bit more risky, which is an interaction of the activity with pre-existing deep fault. And of course, this can bring to larger earthquakes. So here you can see a map of all the induced earthquakes around the world. Unfortunately, it's not really up to date, but you can see in dark orange all the induced earthquakes coming from geothermal energy production. And around the 6% of the induced earthquakes are caused by geothermal energy production. So how does that happen? Which are the causes and factors that bring geothermal energy production to induced earthquakes? So there can be many. One of the most important is the increase in pore pressure, which of course will bring the stress state of the fault closer to the failure envelope, bringing to the nucleation of an earthquake. We can have volume changes, we can have stress transfer, and also other factors of, that can influence the induced seismicity, such as fault geometry, fractures heterogeneity, and also the unfault pre-stress distribution. And lastly, the fluid rheology. So for example, how the properties of the fluid can influence the nucleation and propagation of the earthquake. And this last point is what we focus in our work and what I will show you in the next minutes. So unfortunately, it's not always so easy to monitor the stress state of faults in depth. So we can have some indirect observation through seismology, and one way of studying these kind of problems is reproducing these earthquakes in the laboratory. Of course, we can have many assumptions, but at least we can control the initial conditions, and we can have direct measurements of what goes on during an earthquake. So already in the last years, Chiara Cornelio, during her PhD in our laboratory, she really showed how the fluid viscosity is an important parameter that needs to be accounted for when describing fluid-induced earthquakes. So she performed triaxial high-pressure experiments and high-velocity experiments, and she showed that the fluid viscosity, the higher the fluid viscosity, the more the fault gets unstable, so it's prone to instability. And then also she showed that the fluid viscosity would play a role in the co-seismic weakening, activating elastohydrodynamics. And so following up on her work, we continued to study the role of fluid viscosity in a different kind of experiment, so with a different setup, studying how that would influence the dynamic rupture, nucleation, and propagation. And so here now I will show you our setup that is quite simple. So there are basically two blocks of analog material that are pressed one against the other. So it's a biaxial direct shear configuration. And these two blocks are pressed one against the other, and then they are sheared through two pistons controlled by two hydraulic pumps. And then we can add strain gauges and other kind of sensors to monitor at high frequency what goes on during the rupture propagation. So why do we use an analog material? We use in this study PMMA because it's homogeneous and isotropic. Then it has elastic properties that are lower than the ones of rocks. For example, the shear modulus is much lower. That allows to have larger deformation during the experiment, which will be easier to capture with our sensors. And also, given that the nucleation length of a rupture scales with the shear modulus, we will have smaller nucleation lengths, and so this allows us to have a considerably smaller setup, but with which we can still capture all the complexities of the ruptures. Moreover, it's a transparent material. That means that we can use imaging techniques using a camera, as you will see in a bit. So we use strain gauges to measure the strain evolution with time at high frequency, 2 MHz, all along the fault. And we had also two accelerometers that would measure acceleration, slip, and slip rate. As I mentioned, we had also a fast camera recording images of the interface. As you can see, we could have a photoelasticity measurement. So these measurements are possible for materials that are called load-induced by refringent. That means that they are isotropic when the material is free of stress, while under stress they become anisotropic. That means that it will be easy through the camera to follow the rupture front and to image it. And so how the effect of fluid influence the nucleation and propagation of the rupture? So we studied, we performed two sets of experiments, one under dry conditions for increasing normal stress. So as you can see here, ranging between 1.75 and 3.5 MPa. And then we kept it as a control experiment, and then a second set of experiments under lubricated conditions for a constant normal stress, which was 3.5 MPa, but the fault was lubricated with a fluid of increasing viscosities. So the fluid was obtained with a mixture of water and glycerol, so going from 100% water to 99% glycerol. So when the fault is lubricated, we can have different lubrication regimes depending on the roughness of the fault and the normal load applied to it. So we can have boundary lubrication when the load is supported completely by the solid contact, and in this case the friction of the interface is comparable to the friction of the bulk material, in our case of PMMA. Then on the opposite side, you can have full lubrication when a film of fluid covers the whole interface. In that case, the load is supported completely by the lubricated contacts. And in that case, the friction of the interface will be comparable to the friction of the lubricant. And then we can have a mixed conditions, mixed lubrication, for which the load will be supported in part by the solid contacts and in part by the lubricated contacts. And in this case, the friction value will be in the middle, so in between the one of the fluid and the one of the bulk material. So during our experiments, we have two main stages. So in the first one, you apply the normal load and we keep it constant for the whole duration of the test. And then in the second stage, we increase the shear load until the fault reaches the frictional strength and we have occurrence of instabilities. So what you can see here in gray is the evolution of the shear stress, and each of these straps corresponds to one event, which we will call a laboratory earthquake. And then with these two evolution of normal stress and shear stress, we can compute the evolution of the friction, which I call here friction is just a ratio between the shear stress and the normal stress. And you can see that it follows completely the evolution of the shear stress, as expected. Now we can have a look at how the frictional strength, so the peak friction changed for each different event under the different conditions. So here you can see on the left the evolution of the peak friction with the increasing normal stress, which is of course constant as expected. And once the fault was lubricated with our fluids, the peak friction decreased. And it decreased more and more for increasing fluid viscosity. And so if you remember what I just showed you about the lubrication regimes, this is a hint that our ruptures propagated under mixed lubrication, because the peak friction was in between the one of PMMA and the one of fluid. So all the observations that I will show you later on, they will all refer to this specific lubrication condition. So this was the first observation. So now we can have a look at other properties of the ruptures under lubricated conditions. So for example, the nucleation length. So you know that when you have two blocks that shear one against the other, they will not just shear as a rigid block motion, but there will be a rupture that nucleates and propagates along the interface, and only once that rupture propagated completely, then the two blocks are free to move. So it's like if we had a zip, so you need to initiate the rupture somewhere, and then only the zip is completely unzipped, then the two blocks are free to move. And we can have a look at this rupture front through the help of the camera, of the fast camera. So we can use photoelasticity to track the evolution of the nucleation and propagation of the rupture. Here you can see an example of, these are many images stacked one after the other in time. So on the x-axis you can see the position along the fault, along the interface, and on the y-axis the evolution with time. So you can see that in the right side of the fault, there is a first patch that grows with time, it accelerates, and then it propagates dynamically. So what we did for all our events, it was to handpick this propagation front and to compare it for the different conditions. And in particular, what we did, it was to define a nucleation length, which we called the LC, as the first slipping patch that we could observe. And so let's see how that changed for the different conditions. So this is a similar plot to what I showed you before. So on the left, sorry, you can see how this nucleation length changed with increasing normal stress, and it clearly decreased, and this was expected and was already shown by Latour et al. In 2013. And on the right, the nucleation length surprisingly increased, and it reached value around 5 times larger than the dry case. So why is that? So we know that this can be a definition of the nucleation length, so this ratio between the shear modulus of the material and the fracture energy divided by the stress drop basically of the rupture. So you can see on this case, under dry condition, for increasing normal stress, we clearly expect smaller nucleation length. But why do we see increasing nucleation length under lubricated conditions? So this is probably due to the influence of the friction drop. So as I showed you before, for increasing fluid viscosity, we would measure a much lower peak friction, which comes together, of course, with a lower friction drop. And so this is what controls the increase in nucleation length for lubricated ruptures. Now, another property of rupture is, of course, the fracture energy. So the fracture energy is a key quantity that describes the propagation of the rupture through this rupture propagation criterion. So if the energy available around the crack tip is large enough to be equal to the fracture energy of the interface, which is the resistance to crack growth, then the crack is allowed to keep propagating. So one way to quantify the propagation of a crack is to quantify the fracture energy. And we can do this in our experiment through the use of the mechanical data. As I showed you, we had 16 strain gauges located along the fault. And you can see here in red the evolution of strain with time on top of photoelasticity measurement. So you can see that as soon as the rupture front passes by, there is a strain perturbation. And that strain perturbation is caused by the stress intensity factor that travels together with the crack tip. And so we can use linear elastic fracture mechanics to quantify this energy term. So we follow the protocol defined by Svetlicki and Feinberg in 2014, for which we assume our propagating crack to be a mode 2 crack. And we can use linear elastic fracture mechanics to invert the value of fracture energy. So we know that for LEFM there is one main quantity describing the stress perturbation, which is K, the stress intensity factor. And so we can just very easily compute the theoretical prediction expected from linear elastic fracture mechanics, comparing them with our strain and stress perturbation. We can get output a value of stress intensity factor, which we can input in the formula for the fracture energy. So in this specific example, we could obtain a fracture energy of around 0.1 joule per meter squared. This is an example of a rupture, of a dry rupture at 3.5 MPa. So let's see now how this fracture energy changes for the different conditions. So you can see here at the bottom right, the evolution of GC, the fracture energy for all the conditions. So it's around 1 joules per meter squared under dry conditions, and then you can see that it dramatically decreases in case of lubricated ruptures. And that means that under mixed lubricated conditions, it's easier, the crack propagation is much easier, because the fracture energy that needs to be overcome is much lower. Then another aspect of our ruptures are rupture velocity, So through the measurement of photoelasticity, we could measure the rupture velocity, and we can immediately spot 2 different trends. So you can see that all the ruptures propagating under dry conditions, which are the light blue curves, they all accelerate and reach very high values of velocity, reaching the railway speed. While all the others that are the lubricated ruptures, they rather reach a constant value, and then they will eventually decelerate towards the end of the fault or slightly accelerate. So this made us realize that maybe the rupture propagation mode was different for these 2 different kinds of ruptures. And so we investigated this by considering the characteristic times that describe the rupture time, which are the raise time and the duration time. So when these 2 times are equal, that means that the rupture propagates crack-like. That means that once the rupture starts propagating, then it will keep sliding in its wake. On the contrary, when we have pulse-like ruptures, in particular when the raise time is lower than the duration time, it means that there is a healing front propagating at the back of the crack tip that locks again the rupture, and so the rupture will propagate as pulse-like. And so we computed these 2 characteristic times, and we compared them. And so as you can see here in the plot on the right, the evolution of the raise time against the duration time, and you can see in red the 1-to-1 slope. So all the events propagating under dry conditions, they fall all more or less on that slope, meaning that the dry ruptures propagated most likely crack-like. However, all the other ruptures that occurred under lubricated conditions, they fall in the domain for which the raise time is lower than the duration time, meaning that most probably they propagated pulse-like. So this indicates that the reduced frictional strength, as we saw for the lubricated conditions, might induce pulse-like ruptures rather than crack-like ruptures. And so the main conclusions for this main part are that under mixed lubrication conditions, we can have a reduced frictional strength of the fault. That means that we can have an easier fault reactivation. We will have an increase of nucleation length, meaning that a larger part of the fault will start slipping seismically before to propagate dynamically. Then we notice the decrease of fracture energy, meaning easier rupture propagation, and then the mixed lubrication condition can induce pulse-like ruptures. So now we can have a quick look to how the frictional weakening can affect the rupture dynamics. As Cornelio, the work of Cornelio showed, the presence of high viscous fluid can enhance the weakening behind a rupture under given conditions. So we we try to see how this enhanced weakening could influence the rupture propagation. So already in our experiments performed under dry conditions, so these are all experiments or ruptures performed under dry conditions, we noticed an increased frictional weakening behind the rupture tip. So you can see on the left the evolution of the shear stress on the fault with slip, and the different colors show a different rupture velocity. So you can see that the shear stress never really reaches a constant value, meaning that there is always a bit of a frictional weakening occurring in the way of the crack. And this effect will only be accentuated in case of fluids and fluid weakening, fluid-induced weakening. And of course, this can be reflected into the evolution of the fracture energy with slip that you see on the right. So this fracture energy on the right is just the integral of that curve. So it's basically the area under the curve. So you can see that after a first increase, then the fracture energy keeps increasing with slip without never reaching a constant value, a plateau. So we took these experiments, and we this was the inspiration to do some numerical simulations for which the constitutive law of our fault was a dual weakening law. So not only a first weakening given by the fracture energy of the fault, but a second weakening representing a frictional weakening or fluid-induced weakening, such as thermal pressurization, for example. And so we did two kind of simulations. First, so we put a stress barrier along our fault, and we performed two experiments. The first one with a single weakening friction law, and in that case the rupture stopped at the barrier, as you can see here on the right plot in dash white. So at the position of the barrier, the rupture stopped because the energy available was not high enough to overcome the barrier. However, when we performed the second experiments with the dual weakening law, so and in this case we had a much larger available energy, that you see that the rupture slows down for a bit and then keeps propagating, meaning that an increased weakening in the wake of the crack tip can help the rupture to overcome barrier to keep propagating more and more. Yeah, so this is a schema that I just showed you. So it can a stress barrier can temporarily stop the rupture, but if you have continued weakening in the wake of the crack, then this can be accumulated and help to gain again energy release rate to overcome the stress barrier and the fracture energy that is related to it. And so as a conclusion for this second part, enhanced frictional weakening can influence the rupture dynamics and their given conditions. And when the presence of fluid activates weakening mechanisms, then the rupture propagation can be affected by that.
Yes, thank you for this nice presentation and very original, interesting results you presented to us. I have a question about, you talked about healing fault. So healing generally in fault is understood related to some chemical processes that make the fault recovery, its cohesion, strength, and so on after a seismic event, after damage. And your experiments are very fast, so chemical processes are not time to make effect. So what is the nature of, what could be the nature of this healing process?
Yeah, thank you for this question. I guess that the physical processes could be more related to cohesion, adhesion forces, rather than chemical. So the pulse-like nature of the rupture is mainly controlled by the initial pre-stress. So when the pre-stress before the initiation of the rupture is very low, then there is not enough energy to for the rupture to propagate crack-like. And so I think it would be mostly a nature of energy rather than so the stress is not high enough to feed the rupture, that it will just keep propagating.
So maybe it is a structural effect. So after a first event, you have some stress release, and so you will need more time to increase the stress and to make possible following events, something like that.
Yeah, probably. I mean, even the first events that we measure, they all look good, like, but just because the strength of the fault is much more reduced with respect to the dry case, then there is very little stress drop or friction drop available to sustain the rupture.
Okay, thank you.
Yeah, yes, just how did you measure the value of the stress intensity factor experimentally?
Yeah, so you can just go back. So what we did, it was to compute the theoretical prediction for the stress perturbation. So we just, this formula. So how the stress field changes around the crack tip, and then we select the position at which our sensor, our strain gauge is. So we just fix the position, and we fit our the prediction with our experimental data. So basically, it's the white dashed line that you see on that figure. By fitting the theoretical prediction with our experimental data, then we can invert a value of a stress intensity factor.
Just I have a point. When you write this definition for stress intensity factor, you consider that you have a singularity of the stress field that is a function of 1 over a square root of r. And in your experiment, as far as I understood, you have an interface between 2 blocks.
Yes.
And I'm wondering if this definition can be correctly applied to a situation that you have an interface.
Yeah, so this was showed actually by that paper that I mentioned earlier, Svetliski and Feinberg. So it's a Professor Feinberg group, and in this paper they showed that frictional ruptures, they behave as mode 2 crack. With the assumption that the residual stress behind the crack tip is constant. So that's the main assumption behind it.
I think we have one question.
Yes, a question. How do you control the lubrication condition? Because it's quite difficult to control, to repeat the same condition because of the roughness.
Yeah, that's a very good question, and I think it's we were very careful trying to reproduce our experiments, so we tried to follow always the same protocol. So the fault was lubricated by just dropping some, like a given number of drops at equidistant space, and so we tried to be consistent, but we didn't really have, so the blocks are quite big, so we didn't have a way to really measure the roughness at before every experiment. We just try to do our best.
This is why there are different points.
Yeah, they are a bit scattered, yeah. But those points, they are within the same experiment. So
Okay, I think there was one last question.
I was wondering about the viscosity, because you set a constant value for the viscosity for each test, so it means that your fluid be like a Newtonian fluid. But if you are sharing, do you think that maybe the share, or maybe I don't know, the temperature inside your fort can change the viscosity. That can be maybe more Newtonian fluid than Newtonian.
Yeah, that's a very good question. I don't know, never thought about it. Yeah, probably. I really don't know.
Okay.
Yeah. I will think about it.
Okay.
I don't know.
Okay, thank you.
So I will try to make it light and don't go into too much details. More providing an overview on let's say fluid-driven fractures and their application for reservoir stimulation for geothermal energy, and try to maybe clarify a bit some of the two mechanisms that people have in mind for geothermal development, either hydraulic fracturing or hydraulic shearing, and some of the confusion behind these two. But because it's late in the day, we can start by looking at pictures. Try to put lots of pictures. And the first one is okay, what a really natural hydraulic fractures look like. So that's an example from a dike in Hawaii. So you see emerging at the surface the trace of an hydraulic fractures. It's a magmatic one. Pretty dramatic case of it, and in that case you always have some crazy geologists that go and look at it. So this is an helicopter shot of taken, and they went and landed close to it. So you can, I don't know if you can see, but there is a line, a trace line arriving here, and they went and see and look at the tip of the fractures. And they see it coming at them. So it's very slow. It's quasi-static fractures. Hydraulic fractures are not unstable. They propagate very slowly, and they are volume controlled by the viscous flow inside the crack. You can see. So at some point, I think they started to run away because it was becoming a bit too close. There's a number of interesting features on the mechanics that I could, discuss more at a small scale of the tip. But then after, when you zoom out, you see this is a very linear, hydraulic fractures over kilometers. So that's natural fracking in a sense. And after, when they cool down, they look like that. So they cool down and they get eroded with time. And this is an example in New Mexico, where you have this, in Shiprock, you have this set of dikes that emerge from a magmatic source. And you have a kilometer, I mean, it's, I don't know, it's probably 10 kilometers long. You can follow the hydraulic fractures, and it has been, the magma has cooled, so you can touch it and look at the details of it, but it's extremely planar. So really mode 1 textbook tensile fractures, with, of course, you can see a little bit of complexity, and we can discuss about this, but it's really mostly mode 1 hydraulic fractures. So in the context of application, when we want to extract or inject fluid at depth, we always need a wellbore, and we need to connect the reservoir, being able to inject at economical rate. And the fractures are clearly the preferred flow paths, in the underground, and you can enhance them. You can even do hydraulic fracture to increase the size of your well, in a sense, or do hydraulic shearing. But there is also a notion that is always behind in terms of prevention. You want to keep control of these fractures, or even in the case of CO2 storage, you really don't want to have such a fracture coming in your system. Well, maybe near the well if you want to increase the injectivity of the well, but definitely not at the level of the cap rock or at the level of some faults. And the problem that we all know is that we have a wide range of conditions. So the stress, the material properties, and so the response of this system can vary widely. And the problem is that we are intrinsically data limited. We have very little, geomechanical data. Usually, the stress field is often very poorly constrained. And so, when I see lots of people doing verification of models on field observation, I just shy away because, in my opinion, this is no verification at all. You can feed the elephant whatsoever. Okay. So that's why you need precise and controlled lab experiments, like for example, what showed Federica. Well, you can really control what's going on in order first to understand, to predict, and also after to validate, but you validate on the lab experiments that are properly controlled. So in my research group, we do a lot of modeling. But not only doing the numerical modeling is just not enough. You need to understand and do scaling and dimensional analysis. That's really the key point, to understand the wide variety of the way these fractures actually grow. So we do numerical simulation. I'm going to go back to this numerical simulation of an experiment that was performed where they were driving two hydraulic fractures on the same plane, and the hydraulic fracture coalesced at some point, as you can see there. And at the same time, we want to remain a bit honest, so we decided to do lab experiments so that we could at least keep some connection to reality and actually check the model with experiments. So application for geothermal energy, and in my view also CO2 storage or underground storage, there is a lot of similarities. It's all about enhancing the permeability. So via hydraulic fracturing or hydraulic shearing, I'm going to come back to the difference with that. You want to have a well where it's the easiest possible to inject, so with a low pressure drop. And you will want to do that for CO2 storage as well, because the amount of volume of CO2 that you will have to inject, it's not going to happen without hydraulic fracturing your well, because you need to have very high injectivities. So we're going to inject fluid in rocks, we're going to increase pore pressure, and we're going to fail them. Okay, there's always going to be localization. We know tensile mode and also shear mode, okay, shear bands. So the tensile hydraulic fracture I showed you, this is what is called as hydraulic fracturing. It's purely tensile, and what Federico was discussing is the shear cracks, okay, on pre-existing faults, and they can be triggered by fluid injection as well. So if you want to just look at the two end members, there is these two very different modes of fluid-driven ruptures. On one hand, the tensile hydraulic fractures. So in that sketch, I show that the fluid pressure in blue is larger than the minimum in situ stress, okay? And you basically you do open mode hydraulic fractures. If you want to regain or retain the permeability of these fractures, well, when you stop the injection, the fluid will eventually leak out completely into the rock formations. You're going to close them back. So you want to prop them. So typically you inject sand in the mix in order to keep them open. They have a widely different type of propagation regimes. There's lots of competition between the viscous flow in the crack and the fracture toughness. Okay, and they can grow at in a very different velocity and pace. But they're always quasi-static. You have to imagine it's some meter per second at most. And these fractures are relatively well understood. By that I mean that we have very nice, very well controlled lab experiments, which the prediction are actually matching exactly without any fitting or anything. You just take the parameters, you just do the run, you compare with experiments, it just works. Okay. I quote well because there is still some stuff we don't understand. We can discuss about this, but in model material, I would say we understand the mechanics of that. On the other end, there is the one where you keep your injection lower than the minimum stress. So the fluid pressure is lower than the minimum stress, and then you have, of course, some preferred discontinuity in your rock mass that are oriented favorably with respect to the stress field and the friction coefficient of this interface. And you're gonna activate them in shear. Okay, so you're gonna create a shear crack, And eventually, of course, there is always going to be a bit of dilation. Dilation will eventually cap off. Okay, you go to at some point to a critical state. And here again, as I will show, there is widely different propagation regime for this type of cracks. Okay, and so in the oil and gas industry, in a lot of places, when you do well stimulation, when you want to do something engineered, you do tensile hydraulic fracturing. In the geothermal communities, there's a lot of people that love these shear fluid-driven fractures, trying to say that they will rely on the concept of dilation to increase the permeability of the fractures, so they won't need to inject propane. Okay, and when you hear that, when you've done a lot of well stimulation for plenty of application, you are very doubtful about this because you cannot engineer anything here. You rely on the shear dilation. And there is always only one correlation between an hydraulic fracturing treatment and its success. It's not the stress, it's not the way you pump, it's just the amount of sand you injected. That's the only correlation that actually works. So without injecting materials to remain open in the fractures, it's very doubtful how that could work actually. So well stimulation, in a nutshell, you have this what people call either the inflow performance relationship or the productivity index, just this relation between the flow rate and the pressure drop. So you want to maximize that. You want to have a large flow rate as an injection or production with a minimum amount of pressure drop between your well and your far field pore pressure. And the way, if you have a well, if you do hydraulics, it's all dependent on the hydraulic radius of the well. And the only way you want for the well stimulation is to increase this hydraulic radius. Okay, so people sometimes they do a bit of acid injection to get rid of the near wellbore damage, formation damage around the wells. But the one that is used the most is hydraulic fracturing. So you fracture, you increase your wellbore radius, and you pack sand into it. The other one is hydro shearing. So if we go to geothermal reservoir, so there is these two types that were mentioned previously. So the hydrothermal, so the idea behind the hydrothermal is that it's mostly sedimentary rock at reasonable depths, so the cost of drilling is lower. You have a thermal anomaly, so you have relatively high temperatures at low depths. So example is Tuscany, the Lardarello field in Tuscany, for example, where I think at 300 meters they are already at 100 degrees C. The geysers in the US. This is where it's more like an exploration problem. You have to find a place where you have sedimentary layers and a heat anomaly. Usually it correlates with plate boundaries, of course, for this. And this is the project of geothermal energy which are economically viable are these ones at the moment. They are the only ones that works when they can actually make some money. The other one was a concept that was first thought of in the energy crisis in the 70s, was to say, okay, but if you drill deep enough, everywhere on Earth, you're going to hit 150 degrees or 200 degrees C. And so we can forget about geology and just drill, okay? Interesting enough, at the same time, people were starting to do the same with unconventional gas. They were targeting, okay, instead of finding my usual gas reservoir, I go and drill directly to the source rock, and I produce from the source rock. And that's unconventional shale gas, okay? And they managed to make it work in the 2000s with, intense horizontal drilling on hydraulic fracturing. And in the 70s in geothermal, the first project in Fenton Hill, they tried to do exactly that. They did a well, which was nearly horizontal, and they tried to do an hydraulic fracture. It didn't work for a number of reasons, mostly of hardware, equipment hardware. And so after that, the people in geothermal energies, they start to say, oh, it cannot work. So let's do hydro shearing. So that was the concept that was in geothermal energy since then, in plenty of field application like a pallet site. But it's basically relying on this concept of shear-induced dilation. So You inject, you increase the pore pressure, you lower the effective stress, you activate the fold, you activate the fractures, and you shear dilate them, okay? And you hope that's going to be sufficient to increase your permeability. Honestly, the number of projects that have done it and the success tell you that probably it's not a very, clever idea. But still, some people still think that it can work. So I'm not gonna say anything, but you can imagine what I think. So now I'm gonna talk a bit more on the frictional rupture. Just because so recently we tried to look a bit at the mechanics of that and try to see, okay, how they extend. So in our view also on what people have observed, so Federica mentioned nucleation of earthquakes, but most of these frictional ruptures actually are seismic. Okay, François Cornet in Souls, after stimulation in Souls, showed very well, this very large seismic slip, and so the slip is mostly seismic, and we want to try to understand that a bit better and link it with injection parameter. So on the left, this is what the real faults look like, and on the right, this is my simplification because I'm an engineer. And basically a model, and I quote from this paper from Starfit and Kunda, that the model is a simplification of reality rather than an imitation of reality. And it's an intellectual tool that has to be designed and chosen for a specific task. Okay, and you really have to keep that in mind. You want to ask yourself the questions and why before going into details. And they further go on in that paper that I really recommend everybody that do rock mechanics to read, okay, and read probably every month to keep sane. And they always say, that the design of a model should be driven by the question that the model is supposed to answer, rather than the details of the system that is being modeled. You have a lot of, in my opinion, other complexification for nothing in a lot of work. And by experience, especially related to hydraulic fracturing or this free-driven shear rupture, the overcomplexification of models, they don't lead to better predictability. That is really clear. And I think I was very fortunate actually to work with Pierre. So he was really instrumental for me doing a PhD. I had a class with him before. And because he was really much into that, in the sense that designing mathematical models were simple and clear assumption, and carrying them all the way. So you have to solve them correctly, right? Especially with Pierre, and then check with observation. I'm not trying to put everything in a model, just shake it, and then you don't know what you do. And so I think I try to continue, that approach really, is the most important for me. And Pierre was really, I think, in my opinion, the example of the way you should do modeling in rock mechanics in that aspect. So I'll try to show you how we try also to follow the same philosophy on this very complex problem of aseismic free-driven frictional rupture. So, and we want to ask, ultimately the question that we want to ask in terms of the injection. So if we think, okay, let's try to do hydro shearing, will it work? Would be, okay, what volume do we need to inject, at what rate, what are the pressure, the fluids, how it's going to affect the permeability, can we manage the seismic risk at the same time? That's basically the underlying engineering question we want to address. And of course we have in situ condition, that is critical, the way we inject, and then you have of course the basic physics, the fluid flow that is going to be coupled to solid deformation. That's going to impact a non-local response. And then we have the fault or / the fractures, because we do just a zero thickness plane, so we don't really care if it's a fracture or a fault at our scale. And we want to look at permeability variation. Is it softening? Is it not? Okay, and how that impact the propagation of disruption. So here, initially you have something which is locked. You're going to inject. You relax the pore pressure, and you're going to have a detachment front, so a frictional crack that is going to go. Okay, and we want to understand, the condition of growth of that crack. So we even simplify a bit further the model. At the beginning, we will say, okay, I know that friction is not constant, but I will forget about it for a while. And I'm going to assume it's constant, it's not changing. And I will also assume that my permeability of my fault is also constant and not changing. Because maybe it is, but as a first, as a first approximation, let's see what happens if the fault is actually, constant in its hydraulic properties. Then, when we know that base case, we can complexify it after, and not the other way around, because then you don't know what you're doing. So the equation that we looked at are the following. So we look at a case which is fully 3D. So it's a plane, okay, which is initially locked, okay. We inject at the center, so we assume, okay, we're going to reactivate a fracture by injecting into it. And we assume that the permeability of the fracture is much larger than the permeability of the rock. So you imagine a crystalline rock, okay? So that's going to be the case where most of the flow is going to be only inside the fracture. So that's a strong assumption, but that's the first one we can make, just to understand better the problem. So the flow is confined on the interface, and it's basically a Darcy flow. Then we have elasticity of the bulk. So we can rewrite the elasticity with as a boundary integral equation, or it's just an elastic problem for the two solids. So we can write, the shear stress as function of the initial shear stress plus an effect of the slip, the accumulated slipping time, okay, on the slipping patch. And then we have the criteria of Coulomb's failure. So the shear stress should be lower or equal to the strength, which is the friction coefficient, we assume constant, times the effective stress. So the effective normal stress of the fault. So the effective normal stress is the initial one, so sigma prime 0, minus the pore pressure perturbation due to the injection. Okay? And for the pore pressure perturbation, because we assume the hydraulic diffusivity is constant, when we inject at a constant rate, this is the well-known test solution, where you have the pore pressure disturbance, the characteristic one delta P star is function of the rate, the viscosity of the fluid, the permeability and the width, so the hydraulic transmissivity of the fracture. And it's a self-similar pore pressure disturbance. As long as you inject, you have a self-similar front of pore pressure disturbance that grows, and it evolves as a square root of 4 alpha t. Alpha is the hydraulic diffusivity of the medium. So it's conduction. It's like the thermal condition, except that here alpha is the hydraulic diffusivity of the fluid. So with this set of equations in mind, we can do scaling and dimensional analysis. And when you do that, you find out that the problem depends only on two parameters. The first one is what we call T. It's what we call the fault injection stress parameter. So it's basically the ratio of the initial distance to failure. So F sigma prime 0 is your fault or your fracture strength, okay? And tau 0 is your initial shear stress on your fault. So if this has to be positive, okay? Because else your fault will be unstable without injecting. So of course, we want to have it locked initially. And delta P star is the strength of this injection. Actually, it's F delta P star. So there is a F that should be in front of delta P star. So that parameter T controls if you're initially very close to failure, or maybe you're far from failure, but you inject very, very strongly. So you can take two examples. One case, you're far from failure, 3 MPa, but you inject very, very strongly, like a maniac, 30 MPa, and then you have a value of T of 0.1, or initially you're very close to failure, 0.3 MPa, and your injection over pressure is smaller, it's 10 times smaller, it's 3 MPa. You result in the same value of T, and you're going to get exactly the same response of the fracture, actually, in that case. So these two limits, the limit where T is very, very smaller than 1, which means that either the distance to failure initially is very small or the strength of the injection is very large, this is what we call the critically stressed regime. And the other one, it's the case where initially you are very far from failure or your strength of injection is very small. It's what we call marginally pressurized. Okay? So T is going to govern completely the way the rupture evolves. I'm going to show you in a minute how. And the other parameters that control everything is the quotient ratio. And the quotient ratio is going to control only the elongation of this 3D crack. Okay. The nice things about it is that when the quotient ratio is 0, the ruptures are circular. And you can do analytical treatment of it. So that's, I think Pierre would have loved this trick. And so you can do, for the case of circular rupture, so quotient ratio equals 0, you can do everything analytically. And you can solve these two n numbers. So you have to view that everything is self-similar because the injection, the pore pressure disturbance is self-similar. So it evolves as a diffusion front, square root of 4 alpha t. But you have these two regimes. The first one, this is marginally pressurized. And basically the rupture front is well within the pore pressure disturbance front. Okay? So in that case, we call lambda is the ratio of the rupture front divided by the diffusion front. The diffusion front is 4 square root of alpha t. Okay? And so in that case, we disturb the pore pressure over large distance, and the slip is occurring on a very, very small patch. Okay? The other way around, the critically stressed regime here, this amplification factor is very large, so meaning that the rupture radius is way, way ahead of the pore pressure disturbance. So even though the pore pressure has not increased at all here, we are slipping, okay? Because we are in this critically stressed regime. So that's very, very different cases. What we showed also after is that if you look at the case where the quotient ratio is not 0, the fracture elongates, but actually the area remains the same. So there are quasi-elliptical rupture, and if you take the two semi-axes and you take an average radius, square root of AB, you get exactly the solution for the circular rupture. So the effect of quotient ratio is second order. It's just on the elongation of the shape. So one thing after that is interesting in this context of this geothermal injection, a lot of the time so there is seismicity, and so in that model it's aseismic, right? So you have to view the microseismicity associated with the fact that you have fluctuation of stress, and with any kind of rupture, being tensile or mode 1, maybe they are quasi-static, but you still have microseismicity, you have acoustic emissions at different scales. And but you can also at some point occur a patch which is frictional weakening, and you slip sufficiently that you activate the nucleation lengths that Federica was mentioning, and then you would have a larger event. Okay? And in lots of cases, they have observed that the larger event was occurring after the injection had been done. And this is very important because they have the concept in all this injection in geothermal energy of what they call traffic light system. So they monitor the seismicity, the microseismicity, and if it rises too much, then they stop pumping. Okay? But they did that, for example, in Basel. They stopped pumping, but then the biggest earthquake occurred. Okay? They did that in Pohang, in North Korea. Well, actually, they didn't even do traffic light system there. They just tried to inject. They could not inject too much, or then they stopped. And 3 months after, they had a magnitude 5 earthquakes in a place where there were no earthquakes before. Okay. So we looked at what happens when you shut in. So when you shut in, so when you inject, you have this kind of rupture. They are crack-like. Okay, they elongate, crack-like. And when you stop injection, so the pressure at the well will drop. You will relock. So we'll have the patch that will relock. So you'll have a locking front that moves from the well, and that will eventually catch up the rupture front. But the rupture front is still growing, okay? Because it's driven by pore pressure diffusion and stress transfer, which is following the pore pressure diffusion. And so you can carry on the rupture for quite a while before it stops, and you accumulate more slips. You eventually have a zone of the fracture that is more perturbed, and you have more probability of hitting a spot which is frictional weakening. Okay? So the results of the simulation look like that. You can scale them by the time at which you stop pumping. So TS is the shutting time. And here you have the radius of the rupture in black, okay, scaled by the rudder at shutting. You have also in blue what is called the pore pressure back front. I will explain you what it is in a minute. And in red, it's a locking front. Okay, this is a front that is locking. So you see immediately when we shut in, the locking front accelerate is faster than the rupture front, but the rupture front still grow. So you can see here in that example, it's for a value of T of 0.15. You have 40% more area that is slipped than what it was at shut-in. And it went on for 7 times the duration of the injection. So if you inject for 1 day, that means for 7 days, you will sleep in that case. So eventually, as the locking front is faster than the rupture front, it catches and it arrests. So what drives it is, of course, you stop your injection at the well, so the pressure at the wellbore drops, but the peak pressure, the peak pore pressure, is moving inside the domain, okay? And this is what we call the pore pressure back front. And this, at some point, at the time of arrest, the 3 front coalesce, which is kind of a nice property. So with that, you can just span your parametric space again. So it's only function of this T parameter and the quotient ratio, but let's assume we can factor out the quotient ratio. So these are the evolution. So T and radius, so time of arrest at the top, radius of arrest at the bottom. So you see, if you have a value of T of, so quite small, here 10 minus 3, basically the time of arrest is 2000 the time of injection. So here maybe you've injected only for 1 day, but the sleep will go for 10 years. So it's extreme, but that's it. Other end, which is very interesting, is this end. So when you are marginally pressurized, in that case, you see that basically you automatically stop. So you stop injecting, you stop immediately, the fracture arrests immediately, and nothing happens. And in between, you see very quickly you get to this asymptote, which is a like inversely linear relation between arrest time and the value of T. For the arrest radius, it's departing a bit more from linearity earlier, but you can get so the maximum one was 1.8, but it's very easy to get 40% the radius of sleep that you had at shut-in. So what it tells us is basically even if you shut in the well, the aseismic rupture will continue to grow quite far, and you will eventually probe a larger area of your fracture, of your fault, and you have, of course, more probability of hitting a patch which could go unstable. And there is lots of documented case of this. I took the oldest one. It's the Denver earthquakes in the 60s. That's basically the US Army was injecting close to Denver. They were injecting liquid waste. I don't know what it was, but probably not very nice, at 3.7 kilometers. And they had years of micro earthquakes. So in that plot, you see the year, that's the number of quakes here, and that's the wellhead pressure. And they were always seeing a differential between the earthquakes and the wellhead pressure. And they did their own traffic light system, because at some point, the number of quakes raised a little bit too much, and they decided, oh, we will stop injecting. So you see the pressure in the well decrease. The number of quakes originally decreased, but then they had 3 magnitude 5. 1 year after the end of the injection. So 1 year after the end of the injection, they had the highest actually magnitude of the event that they occurred. And this case is, okay, we don't have all the data to model it, but it really smells like the fact that they were critically stressed, and that the rupture of the aseismic front, which way ahead of the pore pressure disturbance and continue for a long time, after the stop of the injection, and eventually destabilize the fault. So I would argue that these frictional rupture, they are nice, but you probably don't want to play with them too much in engineering practice. And for me, the hydraulic fractures are the best fractures. Okay. And you can really engineer them. So here I put a cartoon of what looks the stimulation in oil and gas for unconventional reservoir. And so you can really optimize the process, do multi-stage fracturing, and really drive down the cost of these wells dramatically. That's what the Americans have been doing. One thing that you want to look for is containment of the hydraulic fractures. So I'm going to talk about that a little bit, just to illustrate that this is a very old technique. So it's been optimized. You have 70 years of return of experience on this. And hydraulic fractures, you design them with respect to your reservoir, and so you need always to prop them. Okay, there is this ratio between the fracture transmissibility. So Kf is the transmissibility of the proppant pack, W is the width, and you divide that by the permeability of the reservoir on the half length of the fractures, and everything is related to this. So depending on the reservoir, you want. If the reservoir is very tight, you want very long fractures, and you don't need a lot of fracture conductivity. Whereas if the reservoir is already quite porous, you want shorter fracture but more permeable fractures. So they play out with that. But one of the key problems or the key control you want to have is the fact that it's indeed something like that is happening. So here I made a sketch where the fracture is contained within the reservoir. And the idea is that you have a stress barrier at the top and at the bottom, but it's not always the case. And there's a lot of you really want to control the containment of the fractures. So the vertical hydraulic fracture containment and anisotropy. So this is something we looked at because most of the models they don't really match the observations. In the sense of when there is case studies and the people try to measure the stress profile and they do hydraulic fracturing, we model the treatments, and it always seems to be that the models overestimate the vertical propagation compared to reality. And one smoking gun can be that, okay, the containment is function of material properties, the in situ stress is to first order important, propagation regime as well, but the intrinsic lamination of sedimentary rock was not very looked at. So we looked at that actually. We looked at it from a, let's say, theoretical perspective. So just a bit of advertisement. We have a code that models this type of fractures pretty well, and it's open source. It's for hydraulic fractures, not frictional fractures. We will hopefully soon release one for the frictional fractures. And it's very well validated with existing solution for limiting case of hydraulic fracturing, but also lab experiments. So here it's you remember these lab experiments of these coalescing fractures, and here it's a moment where the two fractures coalesce. So they did that experiments in hydrogel, so they could do optics, get the full width measurements, and you see the full width measurement at the moment. So zooming at the coalescence point of the hydraulic fractures, and this is the simulation, and the scale is the same. So it's not that bad in terms of prediction. But like what you were saying this morning with salt which were refabricated, it's the same. People say, yeah, but you match your thing on PMMA glass or do real rocks. So we went and we were doing real rocks. So we developed a polyaxial frame to do this kind of experiment, which is it's a bit crazy to be honest, but we can get some interesting data. So it's cubic samples, so we can apply the confinement. We have a vertical well. Here you see the well. We run the well all the way through, so we don't create any stress concentration, and we notch it with an axisymmetrical device. So we create we really manufacture the stress concentration to try to promote radial hydraulic fractures from this. And the monitoring, because now it's non-transparent, so we have to move to acoustics. So we do active and passive acoustics. So the active acoustics, we have in total we have 64 sensors around the block. 32 act as source and 32 act as receiver. And we're looking basically at the diffracted wave, the transmitted wave, and the reflected wave. So this idea comes from work that was done in the 90s in TUDEF, where we retook their ideas and tried to actually put more sensors on it. And so if we look at the diffraction, this is what we can get. We can reconstruct with time the diffracted front during the experiment. So we do a scan every 4 seconds in that experiment. Okay. So we repeat the scan and we reconstruct the fracture front. So how do we reconstruct the fracture front? We do it with diffracted waves. So we subtract, we have the base signal, we have the current signals, and we see in the wave trace, so that's the experimental time on the x-axis, and that's the wave travel time during one shot, okay? And we do difference. And when you do difference, you get rid of the first of the direct arrival, and you start to see here these waves, which is a diffracted wave. It's a P wave diffracted into P wave, and then after you can see the P wave diffracted into S wave, okay? So with that, and you spend, and Dong, PhD students spend like a month and a half picking all this waveform, because we have a combination of 32 times 32 trace. So you can imagine there's a lot of image like the one I'm showing that you have to look. And with this, after you can reproduce this image. So it brings a lot of interesting results. I'm not going to discuss about the mechanical analysis, but you can see it in a paper that we put out recently. And then we added the 16 passive sensor. They record continuously at 15 at 10 megahertz, and they are resonant frequency, and we added some broadband, and we do so acoustic emission like what was presented before. So I'm going to show you some results on the slate. So the idea of the slate is that it's laminated, and if you want to reproduce condition, the condition where the fracture is vertical and is crossing the lamination, and we want to see how that impacts the shape of the fractures. So we confine such that we really want to promote the fracture perpendicular to the bedding plane. Okay, we don't want it to deviate. And in that query, I don't know, they were systematic. We received these blocks, and all the blocks, they had a specific feature, like one of the bedding plane, which is highlighted here, was always close to the well in all the blocks they gave us. So in a sense, it was repetitive, but we didn't want it at the beginning, but it was always there. So that's an image of the final acoustic emission. I'm going to try to show it to maybe if I stop it. Maybe at the end. And you see that basically the hydraulic fracture was stopped by this. So you have a few acoustic emission on that side, on the bedding plane actually, but the fracture didn't grow and didn't break through that case. And then if we looked at the top view, okay, so this plane is this stopping plane is highlighted in magenta, and we have here the acoustic emission since the initiation, and you can trace an ellipse of the acoustic emission front, and we also added in dash a prediction from a theoretical model that accounts for the anisotropy and everything. And you see the elongation is developing as the mechanics of when you account for anisotropy is also predicting. So I'm gonna stop here. Just try to summarize a bit all what I said. So the hydro stimulation, so the hydro sharing, the concept relies on what the rock has in stocks for us. Okay, so you cannot inject the latency; it will be what it will be given to you, and because you are doing frictional rupture, you're more prone to some instabilities anyway. and you want to stay away from faults, right? Because that can be really problematic if you nucleate a large events, if you stimulate a large pre-existing discontinuity. So you don't want to inject close to large pre-existing discontinuity. On the other hand, the hydraulic fractures, they can be engineered. Okay, it's been maybe because I worked 20 years on them, but they are the best fractures because you can really control their growth very well. But here again, you have to stay away from faults, okay? Because even though they are tensile mode, they are quasi-static and they don't emit elastic energy. Of course, if you have defect in your rock mass, they will pop up microseismicity. And if you have a big fault and you hit that big fault, trouble will happen. And there is documented cases of hydraulic fracturing treatment hitting a big fault and nucleating an earthquake. So you have to also stay away from the faults. And you want to ensure that you control your vertical growth and do the proper measurements. And so for EGS, actually, a lot of people still in Europe, I think, they think that, still thinking of hydro shearing. It's like failing again and again. But the Americans, being the Americans, they are moving to hydraulic fracturing. There is 2 projects that are currently doing exactly what is done in unconventional gas. So deviated well. In the case of Forge, it's not really horizontal. In the case of Fervo, it's a startup company. They actually drill horizontal. And they do multi-stage fracturing with exactly the same technology that they use in oil and gas. And if you look at Fervo, here they went to full horizontal, relatively large diameter wellbore, and they do multi-stage with slick water and propane. Okay, and they were successful in placing all the fractures they wanted to place. So they did that from one well, and then they drilled the second well through the cloud, through the microseismic cloud. So it's moving quite fast. Actually, in the US, you have every month there is a new project or a new startup that is want to do this. And I'm sure the Americans, being the Americans, they will fail 9 times out of 10, but they will try. They will eventually make it work. They didn't report yet the flow in this project. Well, in Fervo, the one which has the most commercial scale, because the Forge is a smaller scale injection. But I bet they may have something left. So it's kind of back to the future, back to the 70s and to the initial idea of Phantom Hill to do horizontal well and hydraulic fracturing. So I'll stop here and I'll stop with a simulation of a magmatic dike, and I'm happy to take questions.
Okay, questions? Hippolyte?
Yes, I have a few questions. My first question is on the P-Frac. I understand that it's kind of open source solver for fracture mechanics. I want to know who is developing the P-Frac.
Well, we are developing it.
You are team.
Yeah.
In Python.
Yeah.
Does it mean that you are doing a lot of numerical computation in Python? You are team?
Yes, and C++ also behind.
Another question is, have you applied or used this model on a real case study or EGS?
So on a real case, I know that some people did. I know that some oil companies use it to test other fracturing software. But our team, we are not in the business of doing modeling for oil and gas.
So my last question is, I understand that it's for fracture growth. Does it help to generate fracture, something like that, depending on the energy or strength?
So it's really a simulator which is geared toward only hydraulic fracturing.
Fracture growth.
Only hydraulic fractures growth.
Not the initiation.
So the initiation, the way we initiate fractures and the way people in the industry use solver for hydraulic fracturing, they're always going to initiate fracture. You don't want to look at initiation because it's impacted by lots of heterogeneity near your wellbore. Your perforation, your one-year completion, and it's useless to try to model that anyway. And so what people do is they put an initial fracture length, small fractures, and they inject into it. And and you model all. The goal is to model the extent of the fracture, okay, with time, the width, and after for industrial treatments, you want to model how the sand is migrating into the fracture. This is very important. That we don't model ourselves, but you know the industry software model. Yeah.
My very last question. So with your propagation, do you integrate in the model? Do you integrate some copper problem like hydraulic?
Yeah, for sure. It's a fully non-linear cable problem. I could speak for 3 hours on the numerical solution of that problem. it's not trivial.
This is not it.
So I will not do that.
Thank you. Thank you so much.
Any other questions?